Welcome back to Scientific Discovery Hub, where we dive into the mind-bending mysteries of the cosmos. Today, we're exploring one of the most thrilling breakthroughs in modern science: gravitational waves, invisible ripples in space-time, caused by the universe's most explosive events. Imagine being able to hear the aftermath of black hole collisions, neutron star mergers, and even echoes from the Big Bang itself. That's the power of gravitational wave astronomy. And this video will take you on a journey through this revolutionary field. So what exactly are gravitational waves? Picture space-time as a fabric stretched across the universe. When colossal objects like black holes or neutron stars accelerate, especially when they collide, they send ripples through this fabric, much like dropping a stone into a pond. These ripples, predicted by Einstein's theory of general relativity over a century ago, were only directly detected in 2015, opening a brand new way to observe the cosmos. In this video, we'll break down everything you need to know: how gravitational waves are created, from violent black hole duets to fiery neutron star kisses that forge gold and platinum, the groundbreaking technology behind LIGO, which can detect changes smaller than a proton's width, like measuring the Earth's circumference with the precision of a single hair. The mind-blowing implications of these discoveries, including insights into the origins of elements, the fate of the universe, and even hints of quantum gravity. Future missions like LISA, a space-based detector set to unlock secrets of supermassive black holes and cosmic events light years away. Whether you're curious about Einstein's genius, the science of multi-messenger astronomy, or how we're rewriting the story of the universe, this video has something for you. No PhD required, just a sense of wonder. Hit play to dive into the symphony of space-time. And don't forget to like, subscribe, and hit that bell icon so you never miss a cosmic revelation. Together, let's unravel the universe, one ripple at a time. In the boundless expanse of existence, where time and space intertwine in a dance older than memory, the universe hums with a silent music. It is not the kind of song that stirs the ears of human hearing, yet it resonates in the very fabric of reality. A symphony composed by the most colossal forces in creation. Picture, if you will, an ocean so vast it stretches beyond imagination, a sea not of water, but of space-time itself. In this cosmic ocean, every celestial event, from the gentle pulsations of a dying star to the cataclysmic explosion of a supernova, sends ripples cascading through the depth. These ripples, though imperceptible to the naked eye, are the echoes of the universe's most profound secrets. They are gravitational waves, the faintest whispers of cosmic violence and harmony, waiting to be deciphered by those who dare to listen. To grasp the magnitude of this phenomenon, consider the scale of the cosmos. A single grain of sand under a magnifying glass reveals a world of complexity. Multiply that by the number of stars in the Milky Way, over 100 billion, and then by the countless galaxies scattered across the observable universe. Yet, even within this staggering immensity, the ripples we speak of are infinitesimally small. A gravitational wave stretching across the Earth would cause a distortion no larger than the width of a proton. To detect such a minuscule shift, humanity had to build instruments so precise they could measure changes smaller than the diameter of an atomic nucleus. This is the story of how we learned to hear the universe's quietest notes, a tale that began over a century ago with the mind of Albert Einstein and culminated in the first direct observation of gravitational waves in 2015. The discovery was not merely a triumph of technology, but a revelation of the universe's hidden architecture. For centuries, astronomers peered into the night sky through telescopes, gathering photons, the messengers of light that had traveled across eons to reach us. Yet, light, though wondrous, is a limited messenger. It cannot penetrate the dense veils of gas and dust surrounding newborn stars or the event horizons of black holes. Gravitational waves, however, bypass these barriers entirely. They are not absorbed, scattered, or obscured. Instead, they travel unimpeded through the cosmos, carrying with them the raw, unfiltered imprint of the events that birthed them. In this way, they offer a new lens, a new sense to perceive the universe in its most fundamental form. But what exactly are these waves? And how do they arise from the cosmic stage? To answer this, we must return to the theoretical framework that first predicted their existence. In 1916, Albert Einstein, armed with the mathematical rigor of his general theory of relativity, proposed that gravity is not a force acting at a distance, as Newton had envisioned, but rather the curvature of space-time itself. Imagine a rubber sheet stretched taut, representing the fabric of space. If you place a heavy object, like a bowling ball, on the sheet, it will create a depression, a curvature in the surface. A marble rolled near the bowling ball will spiral toward it, mimicking the orbits of planets around a star. This is the essence of general relativity. Mass tells space-time how to curve, and space-time tells mass how to move. However, Einstein's equations also suggested something even more profound. When massive objects accelerate, when they move rapidly or collide, their influence on space-time does not remain static. Instead, the distortions propagate outward, much like ripples on a pond after a stone is thrown in. These ripples, Einstein realized, are gravitational waves. They carry energy away from their source, rippling through the cosmos at the speed of light. For decades, these predictions remained theoretical, a ghostly presence in the equations of physics. It was only in the late 20th and early 21st centuries, with the advent of laser interferometer gravitational wave observatory, that scientists could finally test Einstein's vision. The first confirmed detection of gravitational waves came on September 14, 2015, when LIGO's twin detectors in Louisiana and Washington captured the signal of two black holes colliding over 1 billion light-years away. The event, which lasted mere milliseconds, released more energy than all the stars in the observable universe combined. Yet by the time the waves reached Earth, they had stretched and compressed space-time by less than 1,000th of the width of a proton. The achievement was nothing short of miraculous, a testament to human ingenuity and the relentless pursuit of knowledge. More than that, it marked the dawn of a new era in astronomy. For the first time, humanity had opened a new window onto the cosmos, one that revealed the hidden dynamics of the universe in ways never before possible. As we delve deeper into the implications of gravitational waves, we find ourselves standing at the threshold of profound questions. What do these ripples tell us about the nature of reality? How do they reshape our understanding of the universe's most enigmatic phenomena? And what lies beyond the veil of the observable cosmos, waiting to be uncovered by the symphony of space-time? The answers may lie in the very act of listening, not with our ears, but with the tools of science and the boundless curiosity of the human spirit. To appreciate the significance of gravitational waves, we must consider their role as cosmic storytellers. Every wave that reaches us carries a narrative etched into the fabric of space-time. The collision of two black holes, for instance, is a story of extremes of gravitational forces, so intense they warp the very dimensions of space and time. As these celestial titans spiral toward their inevitable union, they emit gravitational waves that ripple outward, each crest and trough encoding information about their masses, velocities, and the geometry of their dance. By analyzing these signals, scientists can reconstruct the final moments of such mergers, piecing together a three-dimensional map of the event with unprecedented precision. This ability to peer into the most violent corners of the universe has already yielded astonishing insights. Neutron star mergers, for example, are now understood to be the birthplaces of heavy elements like gold and platinum. The gravitational waves from these collisions, coupled with the electromagnetic signals they generate, have confirmed long-standing theories about the origins of the elements that make up our world. Moreover, the study of gravitational waves has provided direct evidence for the existence of stellar mass black holes, objects whose presence had been inferred indirectly for decades, but never observed in action. Each detection adds another chapter to the cosmic saga, enriching our understanding of the universe's structure, history, and evolution. Yet the implications of gravitational wave astronomy extend far beyond individual discoveries. They challenge our very perception of reality. If space-time itself is a dynamic, responsive medium, what does that mean for our understanding of the cosmos? Could there be other forms of matter or energy that interact with space-time in ways we have yet to comprehend? Might gravitational waves hold clues to the unification of quantum mechanics and general relativity? the holy grail of modern physics. These are not idle speculations, but questions that drive the next frontier of exploration. As we contemplate these possibilities, we are reminded of the humility required to navigate the unknown. The universe, in all its vastness, remains a mystery, both humbling and exhilarating. The detection of gravitational waves is not the end of the journey, but the beginning of a new dialogue between humanity and the cosmos. It is a reminder that the universe is not a static backdrop for our existence, but a living, breathing entity, constantly revealing itself to those who dare to listen. And so, the search continues. New observatories are being built, from the ground-based Virgo and Kagra detectors to the planned space-based LISA mission, which will orbit the Sun and detect gravitational waves at lower frequencies. These instruments promise to expand our view of the gravitational universe, uncovering sources that current technology cannot reach. With each passing year, the symphony of spacetime grows richer, offering new melodies to decode and new harmonies to explore. But what of the ultimate source of these ripples? The cosmic events that set them in motion. To truly understand the universe, we must turn our gaze to the most extreme phenomena it harbors. Among these, none are as dramatic or as profound as the collision of black holes. These invisible behemoths, with their event horizons swallowing all light, are the architects of some of the strongest gravitational waves ever detected. Their mergers are not merely explosive, they are transformative, reshaping the very structure of space-time in their wake. To follow the story of gravitational waves is to follow the story of black holes, those enigmatic entities that defy our intuitions and push the boundaries of our understanding. Thus, as we stand on the precipice of this new era in astronomy, we are called to embrace both the wonder and the responsibility of discovery. The ripples in space-time are more than scientific curiosities. They are invitations to reimagine our place in the cosmos. They remind us that the universe is not a silent void, but a vibrant, resonant expanse, alive with stories waiting to be told. And as we learn to listen more closely, we may find that the answers we seek are not in the stars themselves, but in the spaces between them, in the delicate, invisible threads that bind the universe together. In the vast, dark expanse of the universe, where light itself is swallowed by the voracious maw of gravity, a dance unfolds, one that defies the senses yet reverberates across the fabric of reality. Two black holes, born from the collapse of ancient stars, are drawn together by the inexorable pull of their own gravity. They do not whirl with the grace of ice skaters or the elegance of celestial tides. Instead, they spiral in a death spiral, their orbits tightening with every passing moment. No light escapes their event horizons, no visible sparks betray their fury, yet the cosmos bears witness to their union through a different medium: gravitational waves. These ripples in space-time, predicted a century ago by Albert Einstein's equations of general relativity, are the only audible echo of this cosmic finale. Imagine, if you will, a universe where sound is not measured in air vibrations, but in the stretching and compressing of space itself. The black holes, locked in their fatal embrace, send out concentric waves of distortion, like the tremors of a stone dropped into a pond, but on a scale so immense that the ripples travel billions of light years before reaching Earth. The final moments of their collision are a crescendo of pure energy, a symphony composed of forces so alien to human comprehension that they transcend the boundaries of sight and sound. This is not merely destruction, it is creation, transformation, and revelation. In the silence of their merger lies a story of the universe's most extreme physics, a tale etched into the very geometry of existence. To stand at the edge of such an event is to confront the limits of human perception. We cannot see these black holes, nor hear their screams, yet their presence is undeniable. Their gravitational waves, detected by instruments like LIGO and Virgo, are the fingerprints of the unseen, the whispers of a cosmic ballet choreographed by the laws of gravity. As we delve deeper into this phenomenon, we begin to unravel the threads of a mystery that has lingered since the dawn of modern physics. How do two of the most enigmatic objects in the universe, when brought together, rewrite the rules of reality itself? At the heart of this celestial duet lies the elegant and terrifying interplay of mass, gravity, and space-time. General relativity. Einstein's revolutionary theory describes gravity not as a force, but as the curvature of spacetime caused by massive objects. A black hole, the most extreme manifestation of this curvature, warps the surrounding universe so profoundly that nothing, not even light, can escape its grasp once it crosses the event horizon. When two such entities form a binary system, perhaps the remnants of a pair of massive stars that lived and died in tandem, they begin a slow, inevitable descent toward each other. As the black holes orbit one another, they emit gravitational waves, undulating distortions in spacetime that propagate outward at the speed of light. These waves carry away energy, causing the orbit to shrink over time. What begins as a leisurely waltz accelerates into a frenetic spin, with the black holes drawing closer and spinning faster in a process known as in-spiral. During this phase, which may last millions of years, the gravitational waves grow stronger, their frequencies climbing as the orbital period shortens. Eventually, the black holes reach a critical point where the curvature of spacetime becomes so intense that their individual event horizons merge, forming a single larger black hole in a violent merger. The final moments of this collision are a cataclysmic release of energy. In the case of the historic 2015 detection by the Laser Interferometer Gravitational Wave Observatory's LIGO, two black holes with masses approximately 30 times that of the Sun collided 1.3 billion light-years away. For a fraction of a second, mere milliseconds, their merger radiated more energy in the form of gravitational waves than all the stars in the observable universe combined. To put this into perspective, the total energy output of the entire Milky Way galaxy in visible light is dwarfed by the explosive burst from this single event. The energy equivalent to 3 solar masses converted into pure spacetime ripples via Einstein's famous equation, E=mc², rippled through the cosmos, distorting the very dimensions of space and time. After the merger, the newly formed black hole is not static but undergoes a brief ring-down, oscillating as it settles into a stable, Kerr-like shape. These oscillations, detectable as damped gravitational waves, provide a unique signature of the final object's properties, such as its mass and spin. The entire process from in-spiral to ring-down lasts mere seconds in the vicinity of the black holes, but due to the vast distances involved, takes eons to reach an observer like ourselves. By the time the gravitational waves arrive on Earth, they have stretched and compressed space by an infinitesimal amount, less than the width of a proton. Yet with instruments capable of measuring such minute deformations, humanity has learned to listen to the universe in a way never before imagined. This detection, made possible by the ingenuity of scientists and engineers who built interferometers with arms kilometers long, marks a triumph of human curiosity. The LIGO team's 2015 observation of GW 150914, the first direct detection of gravitational waves, was not just a confirmation of a century-old prediction, but a window into a realm of physics previously shrouded in theoretical abstraction. It revealed that black holes are not solitary travelers in the cosmos, but often form pairs, their mergers occurring frequently enough to be detected by our instruments. These events, though invisible to telescopes that rely on electromagnetic radiation, have become the new frontier of astronomy, allowing us to map the universe in a fundamentally new way. The detection of gravitational waves from black hole mergers has reshaped our understanding of the universe in profound ways. First and foremost, it validated Einstein's vision of spacetime as a dynamic entity capable of being bent, stretched, and vibrated by the motions of massive objects. For a century, the existence of gravitational waves remained a theoretical construct, inferred but never directly observed. Their confirmation in 2015 was not merely a technical achievement, but a philosophical one, affirming that the cosmos operates according to principles far stranger and more intricate than those of Newtonian mechanics. Beyond verifying general relativity, these observations have revolutionized our knowledge of black holes themselves. Prior to LIGO's discoveries, our understanding of these objects relied largely on indirect evidence, such as the X-rays emitted by matter spiraling into them in binary systems, or the gravitational influence they exert on nearby stars. Gravitational wave astronomy has provided a direct census of black holes, revealing that they come in a variety of sizes, From the relatively modest stellar mass black holes to the supermassive behemoths lurking at galactic centers. More surprisingly, LIGO has shown that binary black holes are far more common than previously thought, with mergers occurring roughly once every few tens of thousands of years in a volume of space, encompassing a few cubic gigaparsecs. This ubiquity raises critical questions about the origins of binary black hole systems. Do they form from pairs of massive stars that evolve together, eventually collapsing into black holes? Or do they arise dynamically in dense stellar environments, such as globular clusters, where gravitational interactions combine two black holes into a binary? The answer likely lies somewhere in between, with multiple formation channels contributing to the observed population. The spin orientations of merging black holes, for instance, may provide clues. If their spins are randomly aligned, it suggests a chaotic, dynamical origin. If they are preferentially aligned with the orbital plane, it hints at a quieter, isolated binary evolution. Such distinctions, though subtle, offer a glimpse into the life cycles of stars and the environments in which they die. Moreover, the energy unleashed in these mergers has implications for cosmology. Gravitational waves serve as standard sirens, a term analogous to standard candles used in measuring cosmic distances. By combining the measured amplitude and frequency of gravitational waves with the redshift of the host galaxy, astronomers can independently determine the distance to the source. This method, still in its infancy, holds promise for refining measurements of the Hubble constant, the rate at which the universe is expanding, and for probing the nature of dark energy. Future detections may even reveal intermediate mass black holes, a mysterious class of objects that could bridge the gap between stellar mass and supermassive black holes, shedding light on how the largest structures in the universe form. Yet, for all the answers gravitational waves have provided, they have also deepened the mysteries of the cosmos. Why do some black holes merge with near-perfect symmetry, while others exhibit dramatic asymmetries? What role do these mergers play in the distribution of mass and energy throughout the universe? Could the gravitational waves from the earliest black hole mergers, imprinted in the fabric of spacetime shortly after the Big Bang, still be detectable today? These questions, and countless others, remind us that the universe is not a static puzzle to be solved, but a living, evolving entity that continually defies our expectations. The study of black hole mergers is not merely an academic pursuit. It is a testament to the resilience of human curiosity. In the face of the unknown, we build instruments of exquisite precision, refine our theories, and peer into the abyss, not to conquer it, but to understand it. And in doing so, we find that the universe, for all its indifference to our fleeting existence, is not silent. It sings in the language of gravity, and we at last have learned to listen. While black holes reign supreme in the gravitational wave landscape, another class of cosmic entities adds a dazzling counterpoint to the universe's symphony: neutron stars. These ultra-dense remnants of supernova explosions, forged in the crucibles of dying stars, are among the most extreme objects in the cosmos. Unlike black holes, whose gravitational pull is so strong that not even light can escape, neutron stars retain a tenuous grip on reality. Their surfaces glow faintly with electromagnetic radiation, and their interiors harbor matter compressed to densities exceeding that of atomic nuclei. Yet, when two neutron stars spiral into each other in a binary system, they produce not just gravitational waves, but a brilliant explosion of light, a kilonova that can outshine entire galaxies for a fleeting moment. The 2017 detection of GW 17017, the first observed merger of two neutron stars, marked a watershed moment in astronomy. Unlike the silent, lightless collisions of black holes, this event was a multi-messenger spectacle. Gravitational waves were followed within seconds by a gamma-ray burst, and in the days and weeks that followed, telescopes across the electromagnetic spectrum, ranging from radio to optical to X-ray, captured the aftermath of the merger. This confluence of signals heralded the dawn of multi-messenger astronomy, a new era in which the universe is studied not through a single lens, but through the interplay of gravity, light, and particles. Neutron star mergers differ from black hole mergers in both their physical processes and their observational signatures. Where black holes vanish into darkness, neutron stars, with their electrically charged, rapidly spinning surfaces, generate magnetic fields so powerful they can accelerate particles to near-light speeds. These fields, combined with the extreme tidal forces during the inspiral, create a cascade of high-energy phenomena, jets of relativistic particles, bursts of neutrinos, and the synthesis of heavy elements, like gold and platinum, through the rapid neutron capture process, our process. The kilonova resulting from GW 170-117, for instance, was observed to be rich in these elements, offering conclusive evidence that such mergers are the primary cosmic forges of the heaviest elements in the periodic table. The transition from black holes to neutron stars is not merely a shift in the type of objects involved, but a leap into a realm where the laws of physics are tested under conditions that cannot be replicated in laboratories. Neutron stars challenge our understanding of nuclear matter, quantum chromodynamics, and the behavior of matter at densities approaching that of a black hole's singularity. Theorists grapple with questions such as, what is the maximum mass a neutron star can support before collapsing into a black hole? How do magnetic fields influence the dynamics of a merger? What role do these events play in the chemical evolution of galaxies? As we turn our gaze to the next chapter of gravitational wave astronomy, the dance between black holes and neutron stars reveals a universe teeming with complexity and wonder. While the former teach us about the ultimate fate of space-time, the latter illuminate the alchemy of the cosmos, forging the very materials from which planets, life, and even the atoms in our bodies are built. In the coming decades, as observatories like the Laser Interferometer Space Antenna, LISA, and next-generation ground-based detectors come online, we will witness a richer tapestry of cosmic duets, each collision a note in the universe's eternal song, each merger a reminder that destruction and creation are two sides of the same cosmic coin. In the vast, silent expanse of the universe, where time and space bend under the weight of gravity's invisible hand, two objects orbit each other in a slow, inexorable waltz. These are neutron stars, remnants of stars that once burned fiercely before collapsing under their own gravity, leaving behind city-sized spheres of unimaginable density. Each neutron star is heavier than our sun, yet compressed into a sphere barely larger than Manhattan. To imagine their collision is to envision a symphony of destruction and creation, a cosmic ballet that ends in a cataclysmic embrace. As they spiral closer, their gravitational fields warp the fabric of space-time itself, sending ripples outward like waves across a pond. Yet this is no ordinary explosion. It is a crucible of transformation, a forge where the heaviest elements of the periodic table are born. From this violent union emerge elements that define our world. The gold in wedding rings, the platinum in catalytic converters, the uranium in nuclear reactors. These atoms, scattered by the force of the collision, travel across galaxies and eventually become part of planets, oceans, and living beings. Every time you hold a piece of gold jewelry or use a device powered by rare earth metals, you are cradling the legacy of a neutron star merger. Such events are rare, occurring roughly once every million years in a galaxy like ours. Yet their consequences ripple through time and space, shaping the chemical composition of the cosmos. They are not merely celestial phenomena. They are the engines of existence, the alchemists of the universe. To witness one of these collisions is to stand at the intersection of physics, chemistry, and poetry. The light emitted in the aftermath glows with the fingerprints of newly forged elements, while gravitational waves hum a song older than time itself. In the 2017 detection of GW 170-017, humanity finally heard this song and saw its echo, bridging the gap between theory and observation. But what lies at the heart of this cosmic alchemy? How do two dying stars give birth to the building blocks of life? And what does their story tell us about our place in the universe? When two neutron stars collide, they unleash an energy greater than the combined output of all the stars in the Milky Way over 1,000 years. This explosion, known as a kilonova, is a fleeting but incandescent burst of radiation, unlike supernovae, which rely on the collapse of massive stars. Kilonovae derive their power from the rapid release of neutrons, a process so extreme it defies earthly comprehension. At the heart of this phenomenon is the R process, or rapid neutron capture, a sequence of nuclear reactions where atomic nuclei absorb neutrons faster than they can decay. This process creates unstable isotopes that later transform into stable heavy elements like gold, platinum, and thorium. The conditions required for the R process are as precise as they are brutal. Neutron stars are composed almost entirely of neutrons, packed so densely that a single teaspoon of their material would weigh billions of tons. When these stars merge, their outer layers are torn apart by tidal forces, spewing neutron-rich debris into space. This debris becomes a cosmic furnace, where free neutrons bombard atomic nuclei in milliseconds. The result is a cascade of transformations. Iron seed nuclei grow into strontium, then barium, then gold, each step climbing the periodic table like a ladder forged in fire. By the time the kilonova fades, the surrounding interstellar medium is enriched with elements far heavier than those produced in ordinary stellar explosions. The discovery of GW-170-117 in August 2017 marked the first time astronomers directly observed both gravitational waves and electromagnetic radiation from a neutron star merger. Detectors like LIGO and Virgo picked up the gravitational waves first, a faint, high-pitched chirp lasting just a few seconds. Moments later, telescopes around the world captured the kilonova's glow in visible light, ultraviolet, and radio wavelengths. Spectroscopic analysis of this light revealed the unmistakable signatures of heavy elements, confirming decades-old theories about the R process. The event occurred in a galaxy 130 million light-years away, yet its echoes reached Earth carrying a message from the dawn of the universe. You are here because of this. What makes neutron star mergers unique is their efficiency. Supernovae, while powerful, produce mostly lighter elements up to iron. The R process requires extreme neutron flux, which is most reliably achieved in the chaotic aftermath of a kilonova. Simulations suggest that a single merger can create as much as 100 Earth masses of gold and 10 Earth masses of platinum. Over the history of the universe, these events have seeded galaxies with the raw materials for planets and life. Without them, the periodic table would be incomplete, and the universe would lack the diversity of matter that enables chemistry in us. The realization that we are made of stardust is not new. Carl Sagan famously remarked that we are star stuff, a phrase echoing the legacy of supernovae, which forge most of the elements in our bodies. Yet the discovery of neutron star mergers adds a deeper layer to this truth. Every atom heavier than iron in our cells, every calcium in our bones, every iodine in our thyroid, every gold fleck in the crust beneath our feet, has a lineage that traces back to a kilonova. We are not merely children of the stars, we are grandchildren of the universe's most violent unions. This revelation reshapes our understanding of cosmic history. For millennia, humanity mapped the heavens by studying light alone. But the 2017 detection of GW-170-07 ushered in an era of multi-messenger astronomy, where gravitational waves, electromagnetic radiation, and even neutrinos work in concert to paint a fuller picture of the cosmos. Gravitational waves, ripples in spacetime predicted by Einstein and first detected in 2015, offer a unique window into events too energetic or obscure to be seen with traditional telescopes. When paired with optical, X-ray, and radio observations, they reveal the full drama of cosmic collisions. The implications of this synergy are profound. For instance, the location of GW-170-17 allowed scientists to measure the expansion rate of the universe independently of existing methods, offering new insights into dark energy. Similarly, the study of kilonovae helps calibrate the abundance of heavy elements in different regions of the cosmos, refining models of galactic evolution. More poetically, it underscores the interconnectedness of all things. The same processes that create stars and planets also shape the elements within us. The line between the cosmos ourselves dissolves when we consider that the oxygen we breathe was born in a star's heart, the carbon in our DNA forged in stellar winds, and the gold in our veins sparked in a neutron star's final kiss. Yet the exploration of kilonovae is far from complete. Questions remain about the frequency of neutron star mergers, the exact mechanisms of the R process, and whether other astrophysical phenomena contribute to heavy element production. Future observatories, such as the James Webb Space Telescope and advanced gravitational wave detectors like the Einstein telescope, will probe these mysteries with unprecedented clarity. Meanwhile, the study of ancient meteorites on Earth offers clues to the early universe's element-forming events, linking our cosmic ancestry to the primordial past. Beyond science, the story of Kilonova invites contemplation. It reminds us that destruction and creation are inseparable, that the universe's most violent acts give rise to beauty and complexity. A neutron-star merger is not a death sentence, but a generative act, scattering the seeds of new worlds and life. In this context, our existence becomes a testament to resilience and transformation. We are the beneficiaries of a universe that refuses to stagnate, a cosmos that turns chaos into order and entropy into possibility. The first direct detection of gravitational waves in September 2015 was a triumph of human ingenuity, a moment when theory became reality. Yet the story of how scientists learned to hear these ripples is as fascinating as the waves themselves. Before LIGO's groundbreaking observation, gravitational waves were a prediction buried in Einstein's equations, an invisible whisper in the fabric of space-time. To detect them, researchers had to build instruments so sensitive they could measure distortions smaller than a proton's width across a distance of 4 kilometers. How did they achieve this? What challenges did they overcome? And what new frontiers await in the quest to decode the universe's most elusive signals? As we turn to the next segment, we embark on a journey into the laboratories and minds of those who dared to listen to the universe in a new way. Their efforts not only confirmed a century-old prediction, but opened a door to a deeper understanding of the cosmos, one that promises revelations about black holes, neutron stars, and the very nature of reality. The next chapter of this story begins with a question: how do you catch a wave that cannot be seen, heard, or touched? On that fateful morning of September 14, 2015, as the sun began its ascent over the horizon, the world was unaware of the monumental event unfolding in the vast expanse of space. At precisely 4:50 a.m. GMT, a ripple from a cataclysmic collision of 2 black holes, separated by millions of light years, reached Earth. This event marked a pivotal moment in history, not merely for the field of astrophysics, but for humanity's quest to understand the universe. The ripples, known as gravitational waves, were detected by the Laser Interferometer Gravitational Wave Observatory, LIGO, a marvel of modern science and engineering. The detectors, strategically placed in Hanford, Washington, and Livingston, Louisiana, captured an incredibly subtle change in the fabric of space-time, a shift smaller than the width of a proton. This minuscule disturbance heralded a new era in observational astronomy, where the very essence of the cosmos could be perceived in ways previously thought impossible. The significance of this detection cannot be overstated. For over a century, Albert Einstein's theory of general relativity had predicted the existence of gravitational waves, yet their elusive nature made them a mere theoretical construct until that fateful day. The successful detection of these waves not only validated Einstein's equations, but also opened a new window into the universe, allowing scientists to observe phenomena that are otherwise invisible to traditional telescopes. In a moment that transcended the boundaries of time and space, humanity achieved a profound connection with the cosmos, listening intently to the whispers of the universe itself. As the data streamed in from the detectors, the scientific community was electrified. The event, which involved the merger of 2 massive black holes, released an immense amount of energy, equivalent to several times the mass of the sun converted into pure energy. This collision, occurring approximately 1.3 billion light-years away, sent gravitational waves rippling through space-time, distorting the very geometry of the universe. The detectors, with their astonishing precision, caught these disturbances, translating the cosmic symphony into a signal that would reverberate through the annals of science. This groundbreaking achievement was not merely a triumph of technology, it represented a paradigm shift in our understanding of the universe. For the first time, scientists could hear the universe in a way that transcended visual observation. The ripples in space-time offered a glimpse into the most extreme environments imaginable, regions where gravity is so intense that even light cannot escape. These waves carried with them the echoes of ancient cosmic events, revealing the hidden dynamics of black holes and neutron stars, entities that had long eluded direct observation. In that moment, as the first gravitational wave was detected, the world stood on the brink of a new frontier in astrophysics. The implications of this discovery were profound, promising to reshape our understanding of the cosmos and the fundamental laws that govern it. It was a humbling reminder that, despite our advancements, there remains an infinite tapestry of mysteries waiting to be unraveled. The universe, in all its grandeur, was speaking to us, and we were finally learning to listen. To comprehend the extraordinary feat of detecting gravitational waves, one must delve into the intricate mechanisms of the Laser Interferometer Gravitational Wave Observatory via LIGO. At its core, LIGO employs a technique known as laser interferometry, a method rooted in the principles of physics that allows for the measurement of minute changes in distance. This technique, inspired by the famous Michelson-Morley experiment, utilizes laser beams that are split and directed along two perpendicular arms, each stretching 4 kilometers in length. The lasers are reflected back to a central point where they interfere with each other, creating a pattern of light that can be analyzed for any variations. When a gravitational wave passes through the LIGO detectors, it causes a distortion in the fabric of space-time, leading to a stretching and compression of the arms at right angles to each other. This subtle alteration in the length of the arms results in a change in the interference pattern of the laser beams. Specifically, the gravitational wave will cause one arm to lengthen while the other shortens, creating a detectable shift in the phase of the light waves. This shift is incredibly small, measured in picometers, which is a trillionth of a meter, yet it is precisely this minute change that LIGO is designed to capture. The sensitivity required to detect such minuscule fluctuations is nothing short of remarkable. To achieve this level of precision, the detectors are housed in ultra-high vacuum chambers, shielding them from external vibrations and disturbances. The mirrors used in the interferometers are suspended in a complex system of pendulums and springs, which further isolates them from seismic activity and other environmental factors. This meticulous design ensures that the only thing affecting the laser beams is the passage of a gravitational wave through space-time, allowing scientists to distinguish genuine signals from background noise. Moreover, the power of LIGO lies not only in its technical specifications, but also in its ability to discern the faintest whispers of the cosmos. By analyzing the interference patterns, researchers can decode the characteristics of the gravitational waves, including their amplitude, frequency, and direction. This information provides crucial insights into the nature of the sources that generate these waves, such as the mergers of black holes or neutron stars. In essence, LIGO functions as a cosmic tuning fork, resonating with the universe's most dramatic events and translating them into data that can be studied and understood. The detection process also involves advanced computational techniques to filter out noise and enhance the signal. Scientists employ sophisticated algorithms that model expected gravitational waveforms, allowing them to compare observed data against these predictions. When a match is found, it confirms the presence of a gravitational wave and provides details about its source. This combination of cutting-edge technology and rigorous analysis has transformed our understanding of the universe, enabling us to witness phenomena that were once considered beyond the reach of human perception. In addition to its role in detecting gravitational waves, LIGO serves as a testament to the collaborative spirit of science. The project brings together physicists, engineers, and astronomers from around the globe, united by a common goal to explore the mysteries of the cosmos. The success of LIGO is not solely a product of its hardware, but also a reflection of the ingenuity and dedication of the individuals who work tirelessly behind the scenes. Their efforts have culminated in a new observational capability that complements traditional methods of studying the universe, opening doors to discoveries that were previously unimaginable. Thus, the mechanics of LIGO represent a harmonious blend of theoretical physics and practical engineering. The observatory stands as a beacon of innovation, illustrating how the pursuit of knowledge can lead to groundbreaking achievements. As we continue to refine our techniques and expand our capabilities, the potential for new discoveries remains boundless. With each gravitational wave detected, we not only validate our theories, but also gain deeper insights into the very fabric of spacetime, reminding us that the universe is filled with wonders yet to be unveiled. The historic detection of gravitational waves by LIGO in 2015 was more than a scientific milestone. It marked the dawn of a new era in our exploration of the cosmos. This breakthrough validated the foundational equations of Einstein's theory of general relativity, which had predicted the existence of these ripples in spacetime over a century earlier. However, the significance of this detection extends far beyond the confirmation of theoretical predictions. It represents a paradigm shift in how we observe and understand the universe, opening a completely new observational window that complements traditional methods of astronomical study. Gravitational waves provide a unique perspective on the universe, allowing scientists to probe regions and phenomena that are inaccessible through electromagnetic radiation, unlike light, which can be absorbed or scattered by interstellar dust and gas. Gravitational waves pass through matter unimpeded, offering a direct view into the most extreme environments in the cosmos. This newfound capability enables researchers to study events such as the mergers of black holes and neutron stars, which emit no light but produce powerful gravitational waves. By observing these events, we gain insights into the dynamics of these enigmatic objects, their formation processes, and the nature of gravity itself under conditions that are otherwise unattainable in laboratory settings. Moreover, the detection of gravitational waves has profound implications for our understanding of the universe's structure and evolution. These ripples in spacetime serve as cosmic messengers, carrying information about the sources that generate them. For instance, the analysis of gravitational wave signals can reveal details about the masses and spins of black holes, shedding light on the population of these objects in the universe. Such data contributes to our understanding of the life cycles of stars and the processes that govern the formation and evolution of galaxies. Furthermore, the ability to detect gravitational waves from distant cosmic events allows scientists to map the distribution of mass in the universe, providing critical clues about the nature of dark matter and dark energy, which remain among the greatest mysteries in astrophysics. The implications of LIGO's detection also extend to the realm of quantum mechanics, where the interplay between the macroscopic and microscopic worlds becomes increasingly apparent. The observation of gravitational waves demonstrates that the universe operates on scales that span from the tiniest quantum fluctuations to the vastness of cosmic structures. This duality invites a deeper exploration of the relationship between quantum mechanics and general relativity, two pillars of modern physics that have thus far proven difficult to reconcile. As we continue to refine our observations and interpretations of gravitational wave data, we may uncover new insights into the fundamental nature of reality, potentially leading to a unified theory of physics that bridges the gap between these disparate realms. Additionally, the detection of gravitational waves has catalyzed the emergence of multi-messenger astronomy, a field that combines observations from different types of signals, including electromagnetic waves, neutrinos, and gravitational waves, to paint a more comprehensive picture of cosmic events. This interdisciplinary approach allows scientists to corroborate findings and enhance their understanding of the universe. For example, the simultaneous detection of a gravitational wave signal and an electromagnetic counterpart from a neutron star merger in 2017 provided unprecedented insights into the processes that occur during such cataclysmic events. This synergy between various forms of observation not only enriches our understanding of individual phenomena, but also strengthens the overall framework of astrophysical research. As we stand on the precipice of this new observational frontier, the possibilities for discovery are boundless. Future advancements in gravitational wave detection technology promise to enhance our sensitivity to these cosmic ripples, enabling the observation of weaker signals and the detection of more diverse sources. This progress will likely lead to the identification of new classes of astrophysical phenomena, some of which may challenge our current understanding of the universe. Furthermore, the integration of gravitational wave data with other forms of observation, will foster a more holistic understanding of the cosmos, allowing us to address long-standing questions of the universe, the nature of dark matter, and the ultimate fate of the cosmos. In essence, the detection of gravitational waves by LIGO represents a transformative leap forward in our quest to unravel the mysteries of the universe. It not only validates our theoretical models, but also equips us with a powerful tool to explore the cosmos in ways that were once deemed impossible. As we continue to harness the potential of this new observational window, we are poised to unlock secrets that have remained hidden for eons, deepening our connection to the universe and expanding the horizons of human knowledge. The whispers of the cosmos, once silent and elusive, are now being heard, guiding us toward a future filled with discovery and wonder. As we contemplate the profound implications of gravitational waves, a natural curiosity arises. How do these ripples traverse the vast expanse of the universe, carrying with them the secrets of distant cosmic events? The very fabric of space-time, once thought to be a passive backdrop for celestial phenomena, is revealed as a dynamic medium that responds to the violent collisions of black holes and the explosive births of stars. Each gravitational wave is not merely a disturbance. It is a messenger traveling through the cosmos at the speed of light, bearing witness to the tumultuous lives of celestial bodies. Imagine the gravitational waves as ripples in an ocean, undulating through the vast cosmic sea, distorting the very geometry of space and time. These waves propagate without being impeded by the intervening matter, allowing them to traverse billions of light years unaltered. They emerge from cataclysmic events, such as the merging of two black holes or the collapse of a massive star, each one imparting its unique signature upon the space-time continuum. As these waves journey outward, they carry with them the energy and information from their origin, offering a glimpse into the hidden dynamics of the universe that are otherwise obscured from our view. The implications of this journey are staggering. Just as sound waves can convey the nuances of a musical performance, gravitational waves transmit the echoes of the universe's most dramatic moments. Each wave tells a story, revealing the characteristics of its source, whether it be the spin of a black hole or the velocity of a neutron star collision. By deciphering these signals, scientists can reconstruct the events that gave rise to them, peering into the depths of time and space to understand the processes that shape our universe. This ability to listen to the cosmos transforms our understanding of astrophysics, allowing us to observe phenomena that were once considered beyond the reach of human perception. Yet, as we ponder the nature of these waves and their ability to traverse the universe, we are reminded of the limitations of our own instruments and the challenges that lie ahead. The quest to detect and interpret gravitational waves requires not only advanced technology, but also a deep understanding of the underlying physics. As we strive to refine our observational techniques, we must also grapple with the complexities of the universe itself, where the interplay of gravity and matter gives rise to phenomena that continue to baffle and inspire us. In the next segment, we will delve deeper into the mechanics of how these gravitational waves behave as they travel through the cosmos. We will explore the intricate dance between the waves and the fabric of space-time, examining how they interact with the universe and what they reveal about the nature of gravity. As we embark on this journey, we invite you to consider the profound questions that arise from this exploration. What can these waves tell us about the universe's structure? How might they influence our understanding of dark matter and dark energy? And ultimately, what secrets lie within the cosmic ocean that await our discovery? The universe is a vast, humming expanse, its secrets etched into the fabric of space-time. Among the myriad phenomena that traverse this cosmic sea, gravitational waves stand apart, not as light or sound, but as ripples in the very geometry of existence. These invisible undulations, born from cataclysmic events like colliding black holes or supernovae, travel unimpeded across the void, slicing through gas clouds, galaxies, and even the densest stellar cores, without scattering or fading. Unlike photons, which may be absorbed by interstellar dust or bent by gravitational lenses, gravitational waves emerge pristine from their birthplaces, carrying undistorted echoes of the universe's most violent moments. They are the oldest messengers in the cosmos, arriving at Earth as whispers from epochs long past. Their stories encoded in the subtle warping of space itself. Imagine a binary system of two neutron stars spiraling toward an inevitable merger. As they orbit each other, they drag the surrounding spacetime into a rhythmic dance, generating waves that ripple outward like concentric circles on a pond. These disturbances, though infinitesimal, ripple across billions of light years, reaching Earth as a faint tremor in the distances between atoms. Yet their journey is not one of silence. Every collision, every collapse, every gravitational upheaval imprints itself onto the waves, allowing us to reconstruct the cosmic choreography of their origin. When the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first confirmed gravitational wave in 2015, a signal from two black holes merging 1.3 billion light-years away, it was as if humanity had finally learned to listen to the universe's heartbeat. This ability to perceive the imperceptible opens a new window into the cosmos. For centuries, we have relied on light to map the heavens, but light has its limits. It cannot illuminate the earliest moments of the universe, nor can it pierce the opaque shroud of the dark ages before the first stars ignited. Gravitational waves, however, transcend these barriers. They offer a way to probe the universe's infancy, to trace the footprints of the Big Bang itself. In this sense, they are not merely ripples. They are bridges to the unknown, threads connecting the present to the primordial. To study them is to trace the history of the cosmos in reverse, unraveling the tapestry of time with a precision no other tool can match. At their core, gravitational waves are manifestations of Einstein's general theory of relativity, a framework that redefined our understanding of gravity as the curvature of spacetime. According to this theory, massive objects warp the geometry of the universe, and when these objects accelerate, such as when two neutron stars orbit each other rapidly, or when a black hole devours a star, their movements generate ripples in the fabric of spacetime. These ripples propagate outward at the speed of light, carrying energy away from the source in the form of gravitational radiation. Though predicted in 1916, their existence remained theoretical until 2015, when LIGO's detectors observed the unmistakable signature of a black hole merger, a fleeting distortion in spacetime that stretched and compressed the lengths of the observatory's 4-kilometer-long arms by a fraction of the width of a proton. What makes gravitational waves so elusive is their vanishingly small amplitude. By the time such a wave reaches Earth, the displacement it causes is minuscule, on the order of 10^21, equivalent to measuring a change in the distance between Earth and Alpha Centauri, 4.37 light-years, by less than the diameter of a hydrogen atom. This requires instruments of extraordinary sensitivity, capable of distinguishing true signals from quantum fluctuations and seismic noise. LIGO and its counterparts, such as Virgo in Italy and Kagra in Japan, achieve this by using laser interferometry. Beams of light travel along perpendicular arms, reflecting off mirrors to create interference patterns. When a gravitational wave passes, it alternately stretches and compresses these arms, altering the interference pattern in a measurable way. The challenge lies not only in detecting these minute shifts, but also in isolating them from terrestrial vibrations, thermal noise, and even the gravitational pull of passing trucks. The polarization of gravitational waves further enriches their story. Unlike electromagnetic waves, which oscillate in transverse electric and magnetic fields, gravitational waves exhibit a unique pattern of stretching and squeezing known as quadrupole polarization. There are two primary modes: the plus-plus polarization, which elongates space along one axis while compressing it along the perpendicular, and the cross polarization, which does the opposite. The combination of these polarizations depends on the orientation of the source relative to the observer. For instance, a pair of orbiting black holes, viewed face-on, will produce a different polarization pattern than one seen edge-on. By analyzing these patterns, scientists can infer the mass, spin, and orbital dynamics of the source. Moreover, the waveform's frequency and amplitude encode a timeline of the event itself, the in-spiral, merger, and ring-down of the collapsing objects. This intricate interplay of physics reveals the universality of gravitational waves. Whether the source is a neutron star merger, a supernova explosion, or the violent churn of the early universe, the waves they emit obey the same mathematical laws. Yet their detection remains a triumph of human ingenuity, demanding not just technological prowess, but also a deep theoretical understanding of spacetime's behavior. As we refine our instruments and techniques, we edge closer to deciphering the universe's most enigmatic signals, turning the faintest ripples into a symphony of cosmic knowledge. The implications of gravitational wave astronomy extend far beyond the observation of individual events. They offer a revolutionary means to explore epochs of the universe that remain shrouded in mystery, particularly the so-called cosmic dark ages. This period, spanning the first few 100 million years after the Big Bang, predates the formation of the first stars and galaxies. During this time, the universe was a vast, featureless fog of neutral hydrogen, emitting no visible light. Optical and radio telescopes struggle to penetrate this veil, but gravitational waves, unimpeded by intervening matter, could carry direct imprints of the processes occurring during this era. For instance, the mergers of primordial black holes, hypothetical objects that may have formed in the universe's infancy, could generate detectable gravitational waves. If such signals are found, they would provide unprecedented insights into the distribution of mass and energy in the early cosmos, shedding light on whether these black holes played a role in seeding the first galaxies. Even more tantalizing is the possibility of detecting gravitational waves from the Big Bang itself. The universe's explosive birth is thought to have produced a stochastic background of gravitational waves, a continuous hum of ripples generated by quantum fluctuations. Inflation, a rapid exponential expansion proposed to solve the horizon and flatness problems of the Big Bang model, would have amplified these microscopic fluctuations into macroscopic structures, leaving behind a fossilized gravitational wave signal. Detecting this background would be akin to hearing the echo of creation, offering direct evidence for inflation and revealing the conditions of the universe at energies far beyond what particle accelerators can replicate. Current and upcoming experiments, such as the BISEP Keck array and the planned LIGO satellite, aim to measure the polarization of the cosmic microwave background for indirect signs of this gravitational wave imprint. Meanwhile, space-based interferometers like the Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, may directly detect low-frequency gravitational waves from supermassive black hole mergers and other cosmic phenomena. Together, these efforts could bridge the gap between the Planck scale, the realm of quantum gravity, and the observable universe, answering fundamental questions about the nature of reality. Beyond the Dark Ages and the Big Bang, gravitational waves also open a new frontier in multi-messenger astronomy. By combining gravitational wave observations with data from electromagnetic telescopes, neutrino detectors, and cosmic ray observatories, scientists can piece together a holistic picture of astrophysical events. For example, the 2017 detection of gravitational waves from a binary neutron star merger, GW170817, was followed by a burst of gamma rays, optical afterglow, and kilonova emissions, confirming that such mergers are the birthplaces of heavy elements like gold and platinum. Future discoveries may reveal entirely new classes of phenomena, such as cosmic strings, hypothetical one-dimensional defects in spacetime predicted by some theories of unified physics, or the mergers of intermediate mass black holes, whose existence remains uncertain. Each detection adds another thread to the cosmic tapestry, revealing the interconnectedness of the universe's grand architecture. Yet the exploration of gravitational waves is not merely an academic pursuit. It is a deeply philosophical endeavor. To detect these ripples is to confront the profound scale and age of the cosmos, to recognize that the light we see and the waves we feel are relics from events that occurred before life existed on Earth. It forces us to grapple with the notion that the universe is not a static stage, but a dynamic, evolving entity, shaped by forces we are only beginning to comprehend. In this sense, gravitational wave astronomy is more than a scientific discipline. It is a testament to humanity's unyielding curiosity and our drive to seek meaning in the vast silent expanse of space. To truly grasp the significance of gravitational waves, we must first understand the medium through which they propagate. Spacetime itself, often treated as a passive backdrop in classical physics, Spacetime is, according to Einstein's relativity, an active participant in the drama of the cosmos. It is not a rigid grid, but a flexible, dynamic entity that bends under the influence of mass and energy. A massive object like a star or black hole does not simply sit within space, it warps the space around it, curving the paths of light and matter in a gravitational embrace. This curvature is what we perceive as gravity, a force that shapes the orbits of planets, the trajectories of comets, and the expansion of the universe itself. But spacetime is more than a stage for gravitational interactions. It is the very foundation of reality. Time, once considered absolute and universal, is now understood to flow differently depending on one's motion and proximity to massive objects. Clocks near a black hole tick slower than those in empty space, a phenomenon known as gravitational time dilation. Similarly, the distances between objects stretch and contract in response to the universe's expansion, a process that has accelerated over the past 5 billion years due to the enigmatic force of dark energy. These revelations challenge our intuitive notions of space and time, revealing them as fluid, interwoven dimensions rather than fixed quantities. As we continue to probe the universe with ever greater precision, the nature of space-time becomes increasingly intertwined with the mysteries of quantum mechanics. At the smallest scales, the smooth continuum of relativity gives way to a frothing, probabilistic landscape governed by quantum uncertainty. Here, virtual particles blink in and out of existence, and the very concept of a fixed geometry begins to dissolve. This tension between general relativity and quantum mechanics, one describing the cosmos on the grandest scales, the other on the tiniest, lies at the heart of modern physics. Resolving it may require a theory of quantum gravity, a framework that could unify the laws governing the universe from the singularity of the Big Bang to the event horizons of black holes. The study of gravitational waves offers a unique vantage point in this quest. By observing how space-time responds to extreme conditions, such as the violent collisions of black holes, we gain clues about its underlying structure. Do gravitational waves exhibit quantum properties? Can their propagation reveal the granularity of space-time at the Planck scale? These questions remain unanswered, but they underscore the profound connection between the cosmic and the subatomic. In seeking to understand the ripples that traverse the universe, we are ultimately unraveling the fabric of reality itself, inching closer to a unified understanding of existence. And so, as we stand at the threshold of this new era in astronomy, we are reminded that the universe is not a collection of isolated phenomena, but a single resonant whole. The gravitational waves that reach us are not just echoes of distant events, they are harmonics of the cosmic symphony, reverberating through the infinite. To follow their trail is to embark on a journey beyond the boundaries of space and time, into the very essence of what it means to exist in a universe that is both vast and intimately connected. In the vast tapestry of the cosmos, the concept of space-time stands as both a cornerstone and a conundrum. For centuries, physicists grappled with the notion of space as a fixed, unyielding backdrop against which the universe played out its events. However, the advent of Einstein's theory of general relativity in the early 20th century shattered this traditional view, introducing a revolutionary framework that treated space-time as a dynamic, flexible entity. Rather than being a passive stage, space-time became an active player in the cosmic drama, capable of bending, stretching, and even tearing under the influence of mass and energy. This radical shift in perspective was not merely theoretical. It redefined our understanding of gravity itself, revealing it as a manifestation of the curvature of space-time, rather than a force acting at a distance. Einstein's equations, elegant in their complexity, illustrated how massive objects could warp the very fabric of space-time around them. Imagine placing a heavy ball on a rubber sheet. The sheet deforms under the weight, creating a curvature that affects the paths of other objects. In this analogy, the rubber sheet represents space-time, and the heavy ball symbolizes a massive object, such as a planet or star. This visualization captures the essence of how mass influences the geometry of space-time, leading to phenomena like the bending of light around massive bodies, a prediction confirmed by observations during solar eclipses. The implications of this new understanding were profound, challenging the long-held belief in an absolute, unchanging space and time. The acceptance of spacetime as a malleable entity marked a significant paradigm shift in physics. It required scientists to rethink their approach to the universe, embracing a framework where the very nature of reality could be fluid and responsive to the presence of matter and energy. This concept was not easily swallowed. It took decades for the scientific community to fully grasp and integrate these ideas into their understanding of the cosmos. The resistance stemmed not only from the inherent strangeness of the theory, but also from the difficulty in visualizing a four-dimensional space-time continuum. Yet, as experimental evidence accumulated, such as the successful prediction of the precession of Mercury's orbit and the observation of gravitational lensing, Einstein's vision began to gain traction. As we delve deeper into the implications of this dynamic space-time, it becomes evident that our understanding of the universe is intricately tied to the nature of this fabric. The realization that space-time can be warped by mass and stretched by acceleration not only transforms our perception of gravity, but also opens the door to exploring the mysteries of dark matter and dark energy, which may further complicate our understanding of the cosmos. Thus, the journey through the fabric of reality invites us to contemplate the very essence of existence, where the lines between the physical and the abstract blur, and the universe reveals its secrets in ways that challenge our deepest assumptions. The curvature of space-time is not a mere theoretical construct. It is a tangible consequence of the presence and motion of mass. According to Einstein's field equations, any object with mass distorts the geometry of the surrounding space-time, much like a heavy ball placed on a stretched fabric would create a depression. This curvature dictates the trajectories of other objects moving within the same region, giving rise to what we perceive as gravitational attraction. In this sense, planets do not orbit stars because they are pulled by an invisible force, but rather because they follow the natural geodesic paths of least resistance dictated by the curved spacetime surrounding the massive object. This elegant yet counterintuitive description of gravity has been validated by countless experiments and observations, from the precise measurements of planetary orbits to the deflection of starlight near the sun. One of the most striking manifestations of this curvature is the phenomenon of gravitational waves, ripples in the fabric of spacetime generated by the acceleration of massive objects. Just as a pebble dropped into a pond creates concentric waves that propagate outward, the movement of colossal celestial bodies, such as neutron stars or black holes, disturbs the underlying structure of spacetime, sending undulating distortions across the cosmos. These waves travel at the speed of light, carrying energy away from their sources and subtly altering the distances between objects as they pass through. Detecting these minute fluctuations has proven to be one of the greatest challenges in modern physics, requiring instruments of unparalleled sensitivity. The Laser Interferometer Gravitational Wave Observatory LIGO and its counterparts have achieved this feat, confirming the existence of gravitational waves in 2015 through the observation of two colliding black holes. This groundbreaking discovery not only affirmed Einstein's predictions, but also opened a new window into the universe, allowing scientists to observe cosmic events that were previously hidden from view. Yet the most extreme consequences of space-time curvature occur in the vicinity of black holes. These enigmatic objects represent the ultimate expression of gravitational dominance, where the density of mass is so great that the escape velocity exceeds the speed of light. As a result, nothing, not even photons, can escape the gravitational pull once it crosses the event horizon, the boundary beyond which no information can reach the outside universe. Within the event horizon, space-time is so profoundly distorted that the very concept of time loses its conventional meaning. At the heart of a black hole lies the singularity, a point of infinite density and curvature where the known laws of physics break down. Here, the equations of general relativity fail to provide meaningful predictions, highlighting the limits of our current understanding. The singularity is not merely a curiosity. It represents a profound challenge to our comprehension of the universe, suggesting that a more complete theory, one that reconciles general relativity with quantum mechanics, is needed to describe the true nature of space-time at its most extreme. The implications of these extreme conditions extend far beyond the immediate vicinity of black holes. They raise fundamental questions about the nature of reality itself. If space-time can be stretched, bent, and torn, what does this imply about its fundamental structure? Is it truly a continuous fabric, or does it possess a granular, quantum nature at the smallest scales? These inquiries lie at the heart of ongoing research in theoretical physics, particularly in the quest for a theory of quantum gravity. While Einstein's general relativity provides an accurate description of the large-scale structure of the universe, it fails to account for the behavior of spacetime at the subatomic level, where quantum effects dominate. The search for a unified framework that can reconcile these disparate domains remains one of the most pressing challenges in modern science. In the next section, we will explore the implications of treating spacetime as a real, dynamic entity and examine the theoretical approaches that seek to bridge the gap between classical and quantum descriptions of the cosmos. The realization that spacetime is not a static background, but an active, dynamic entity, raises profound questions about its fundamental nature. If spacetime can be curved, stretched, and torn by mass and energy, does it behave like a physical substance, or is it a purely mathematical abstraction? This distinction is not merely academic. It shapes our entire understanding of the universe and determines the path forward in the search for a unified theory of physics. At the macroscopic scale, general relativity describes spacetime with remarkable precision, accounting for the gravitational interactions of massive objects and the large-scale structure of the cosmos. However, when we probe the universe at the smallest scales, where quantum effects become dominant, this elegant framework begins to unravel. The incompatibility between general relativity and quantum mechanics becomes starkly apparent, leading physicists to seek new theoretical models that can bridge this divide. Among the most prominent candidates are string theory and loop quantum gravity, two competing frameworks that offer radically different perspectives on the nature of spacetime. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. In this model, the familiar 3 spatial dimensions and 1 temporal dimension are complemented by additional dimensions curled up at infinitesimal scales, beyond the reach of current experimental observation. By extending the number of spatial dimensions beyond the conventional 4, string theory aims to unify all fundamental forces, including gravity, into a single, self-consistent framework. In this approach, gravity emerges not as a force mediated by particles, as in quantum field theory, but as a natural consequence of the geometry of higher dimensional spacetime. The curvature of this expanded spacetime structure influences the behavior of the strings, dictating their vibrational modes, and ultimately the properties of the particles and forces observed in the universe. However, despite its mathematical elegance, string theory remains highly speculative, as it has yet to produce experimentally verifiable predictions that distinguish it from alternative models. In contrast, loop quantum gravity takes a different route, attempting to apply the principles of quantum mechanics directly to the structure of spacetime itself. Unlike string theory, which introduces extra dimensions to accommodate gravity, loop quantum gravity operates within the familiar 4-dimensional framework, seeking to quantize spacetime by describing it as a discrete network of interconnected loops. In this model, spacetime is not a smooth, continuous fabric, but rather composed of indivisible units, akin to the pixels of a digital image. At the Planck scale, the smallest possible length scale in the universe, these loops form a complex evolving lattice that gives rise to the macroscopic appearance of spacetime. This approach leads to a fundamentally different picture of black holes, where the singularity at their core is replaced by a quantum bounce, preventing the collapse into infinite density. While loop quantum gravity offers a compelling alternative to the infinities predicted by general relativity, it faces its own challenges in providing a comprehensive description of the universe, particularly in incorporating the full range of quantum field interactions. Despite the differences between these theories, they share a common goal: to resolve the paradoxes that arise when we attempt to apply general relativity to the quantum realm. One of the most pressing issues is the fate of information that falls into a black hole. According to classical general relativity, anything that crosses the event horizon is lost forever, leading to the so-called black hole information paradox. This contradiction arises because quantum mechanics dictates that information cannot be destroyed, yet the singularity at the heart of a black hole seems to defy this principle. Some physicists propose that the resolution lies in the idea that space-time itself is not fundamental, but instead emerges from a deeper quantum-based structure. In this view, the singularity may not be a true endpoint, but rather a region where our current understanding breaks down, and a more complete theory is required to describe the underlying reality. Beyond the specifics of individual theories, the broader question of whether space-time is a real physical entity or an emergent phenomenon remains open. Some researchers suggest that space-time may not exist independently, but rather arise from the interactions of more fundamental components, much like the properties of a solid emerge from the collective behavior of its constituent atoms. This perspective aligns with certain interpretations of quantum gravity, where space-time is not a fixed backdrop, but a dynamic relational construct that emerges from the quantum correlations between particles. If this hypothesis proves correct, it would represent a radical departure from our current understanding, implying that the universe we perceive is not built upon a pre-existing space-time framework, but is instead woven together by the intricate interplay of quantum processes. These theoretical explorations continue to push the boundaries of our knowledge, challenging long-held assumptions, and revealing the deep mysteries that still lie at the heart of the cosmos. As we refine our models and develop new observational tools, we move closer to answering one of the most profound questions in physics. What is the true nature of space-time, and how does it shape the reality we experience? The ability to detect gravitational waves has transformed our understanding of the universe, offering a novel means of observing cosmic events that were previously invisible to traditional telescopes. These ripples in space-time, generated by cataclysmic occurrences such as the collision of black holes or the explosive death of massive stars, provide a direct glimpse into the most extreme environments in the cosmos. To capture these elusive disturbances, scientists have developed instruments of extraordinary precision, interferometers that measure changes in distance smaller than the width of a proton. The success of these detectors marks a pivotal moment in astrophysics, opening a new frontier in our exploration of the universe. As we refine our ability to observe these cosmic vibrations, we stand on the threshold of uncovering even greater mysteries, including the nature of dark matter, the origins of the universe, and the fundamental structure of space-time itself. In the vast, silent expanse of the universe, where galaxies spiral in slow motion and stars collapse in fiery crescendos, there exists a language older than time itself, a language written in ripples of space-time. These gravitational waves, predicted by Einstein's equations over a century ago, are the faintest echoes of cosmic cataclysms, colliding black holes, neutron star mergers, and the violent birth of the universe itself. Yet to hear these whispers, humanity has built machines of such extraordinary precision that they measure distortions smaller than the tiniest fraction of a proton's diameter. Imagine stretching your hand across the Earth's surface and measuring its curvature with the accuracy of a single human hair's width. This is the feat accomplished by instruments like the Laser Interferometer Gravitational Wave Observatory, or LIGO. This endeavor is not merely a triumph of engineering, but a testament to our species' relentless curiosity. To detect gravitational waves, we must pierce through the veil of quantum uncertainty, thermal vibrations, and the very fabric of space-time itself. The universe, in its infinite complexity, offers no guarantees. It demands that we listen with tools refined to the point of paradox, where the boundary between the macroscopic and the quantum dissolves. In doing so, we are not only decoding the universe's deepest secrets, but also confronting the limits of our own perception. What does it mean to observe a disturbance in space-time, so subtle that it warps the very definition of distance? As we peer into this subatomic symphony, we stand on the threshold of a new era, one where the cosmos speaks to us not in light or sound, but in the silent, rhythmic tremors of existence. At the heart of LIGO lies a design both elegant and unforgiving. Two perpendicular arms, each 4 kilometers long, stretching like the limbs of a celestial compass. Within these arms, mirrors hover in near-perfect stillness, suspended as pendulums within vacuum chambers, so pristine that air molecules are absent. These mirrors are not mere reflections, they are the universe's sentinels, their positions monitored by laser beams that travel back and forth like messengers of light. The lasers, generated by a source no larger than a fist, are split and sent down each arm, bouncing between the mirrors before recombining at a detector. Ordinarily, the beams return in perfect harmony, their peaks and troughs aligning to cancel each other out, a state of silence in the quantum world. But when a gravitational wave passes, stretching one arm and compressing the other by a fraction of an atomic nucleus's width, the delicate balance is shattered. The interference pattern shifts, revealing a signal that is both a fingerprint of the wave and a testament to the universe's hidden choreography. Yet this dance of light and space is fraught with challenges. The mirrors must be isolated from every conceivable source of vibration, from distant earthquakes to the hum of traffic, hundreds of miles away. To achieve this, they are suspended in multi-stage pendulums, each stage filtering out disturbances like a sieve refining gold from ore. Even thermal motion, the random jiggling of atoms in the mirror material, is a threat, demanding materials engineered to minimize heat-induced noise. The vacuum chambers, larger than football stadiums, remove air molecules that might scatter the laser beams or introduce acoustic disturbances. And yet, the most profound adversary lies not in the physical world, but in the quantum realm itself. Heisenberg's uncertainty principle dictates that the act of measuring light introduces unavoidable fluctuations in its properties. To circumvent this, LIGO employs a technique called quantum squeezing, a method that reshapes the quantum noise like a sculptor molding clay. By redistributing the uncertainty between complementary variables, position and momentum, for instance, scientists reduce the noise in the measured quantity, allowing the faint signal of a gravitational wave to emerge from the fog of quantum randomness. This interplay of light and matter is a ballet of extremes. The lasers, operating at powers exceeding 100 watts, must remain stable to within picometers, distances smaller than the diameter of a hydrogen atom. The mirrors, polished to tolerances finer than the wavelength of visible light, reflect the beams with near-perfect efficiency. Every component is a marvel of precision, from the fused silica suspension fibers to the ultra-low noise photodetectors that convert the interference patterns into electrical signals. Together, these elements form a machine that listens not with ears but with photons, translating the universe's silent ripples into data that humanity can comprehend. The success of LIGO is not merely a story of technological achievement, but a revelation of the deep connections between the smallest and largest scales of existence. At its core, the detection of gravitational waves bridges the chasm between quantum mechanics and general relativity, two pillars of modern physics that have long resisted unification. The quantum fluctuations that once seemed like obstacles to measurement now become tools in the quest to understand the cosmos.
32 seconds into the flight,
these fluctuations through quantum
three liquid fuel main engines soon will throttle back to 72% of rated performance down in the bucket, reducing the stress on the shuttle as it goes transonic.
Of space-time. This duality is emblematic of the universe itself, a place where the behavior of individual particles influences the fate of galaxies, and where the ripples of cosmic collisions reverberate through the quantum vacuum. Beyond its technical marvels, LIGO's precision forces us to confront the fragility of our understanding. The ability to measure distances with such accuracy exposes the limitations of classical physics and compels us to rethink the nature of reality. For instance, the detection of gravitational waves has confirmed predictions about the behavior of black holes and neutron stars. But it has also raised new questions. How do these dense objects merge? What happens to the information swallowed by a black hole during a collision? Do the quantum properties of space-time manifest in ways we have yet to imagine? Each answer seems to beget another mystery, as if the universe is a puzzle whose pieces are constantly rearranged by the very act of observation. Moreover, the implications of LIGO extend beyond the scientific community, challenging our philosophical relationship with the cosmos. To detect a ripple in space-time is to witness the universe's memory encoded in its geometry. Every gravitational wave carries a history of violence and creation. The final moments of a dying star, the violent embrace of two black holes, or the explosive birth of a kilonova. These events, occurring billions of light-years away, arrive at Earth as imperceptible distortions, waiting to be decoded by instruments like LIGO. In this sense, the observatory is not just a tool, but a participant in the universe's storytelling, translating ancient echoes into a language we can interpret. The knowledge gained is not static. It is a dynamic dialogue between the present and the past, between the observable and the unseen. Perhaps most profoundly, LIGO's success underscores the power of collaboration across disciplines. Engineers, physicists, and computer scientists have worked in concert to overcome challenges that would have been insurmountable in isolation. The development of cryogenic cooling systems, the application of machine learning to filter noise, and the refinement of materials science to create ultra-stable mirrors all exemplify how diverse fields converge in the pursuit of a common goal. This synergy mirrors the very nature of the universe, where the laws of physics operate seamlessly across scales, from the quantum to the cosmic. In building LIGO, humanity has not only constructed a machine, but woven a tapestry of knowledge that reflects the interconnectedness of all things. Yet, for all its precision, LIGO is not immune to the cacophony of the universe. The signal it detects is but a whisper amid a storm of noise, seismic tremors, thermal vibrations, electromagnetic interference, and the ever-present hum of quantum uncertainty. Separating the signal from this chaos is akin to hearing a single note played on a piano in the middle of a thunderous orchestra. The data produced by LIGO is a torrent of information, requiring sophisticated algorithms and global networks of observatories to discern patterns that might hint at a gravitational wave. This next step in the journey, decoding the signal from the noise, is where the raw potential of discovery transforms into tangible knowledge. It is a process that demands not only computational ingenuity, but also a deep understanding of the universe's many voices. As we turn our attention to this challenge, we enter a realm where the line between signal and noise blurs, and where the true art of observation begins. The universe is a symphony of motion, a ceaseless interplay of forces that shape the cosmos. From the birth of stars to the collision of galaxies, every event sends ripples through the fabric of space-time. Yet, when it comes to detecting these ripples, gravitational waves, they arrive as whispers in an ocean of noise. Imagine standing in a thunderstorm, your ears strained to hear a single syllable spoken by a distant friend. The wind howls, rain drums against the earth, and lightning cracks the sky. In this cacophony, how does one discern the faintest murmur? This is the challenge faced by gravitational wave detectors. Instruments like LIGO, Laser Interferometer Gravitational Wave Observatory, Virgo, and Quadra are designed to capture disturbances in spacetime, so minute that they alter the distance between mirrors, separated by kilometers, by less than the width of a proton. These detectors are, in essence, microphones attuned to the universe's most elusive notes. But just as a storm drowns out conversation, the universe itself is a roiling sea of interference. Seismic tremors from earthquakes, thermal vibrations from the hum of atoms, and even the quantum jitter of light all conspire to obscure the signal. To find meaning in this chaos, scientists must wield tools of extraordinary precision and ingenuity, transforming raw data into a map of cosmic events hidden billions of light years away. This is the art of decoding the cosmic symphony, a pursuit that demands not only technological mastery, but a profound patience for the quiet truths buried beneath the noise. To understand how gravitational wave detectors operate, one must first grasp the nature of the noise they contend with. At the heart of these instruments lies a paradox. The very sensitivity that allows them to detect the faintest ripples in spacetime also makes them vulnerable to a multitude of terrestrial and quantum disturbances. Seismic noise, for instance, arises from the constant movement of the Earth itself. Tectonic shifts, passing trucks, and even the footsteps of researchers outside the vacuum chambers send vibrations coursing through the ground. These disturbances, though imperceptible to the untrained eye, can mimic the subtle stretching and squeezing of spacetime caused by gravitational waves. To mitigate this, detectors are often sited in remote locations, shielded by layers of isolation systems that dampen seismic activity, suspended by pendulums, and encased in active feedback loops. The mirrors within interferometers remain as still as possible, their movements recorded with laser precision. Yet seismic noise is merely the beginning. Thermal vibrations add another layer of complexity. Every material object, from the mirrors to the steel beams supporting the detector, emits heat. This energy causes atoms to jostle, creating random fluctuations in the position of the mirrors. At the nanoscale, these vibrations can drown out the gravitational wave signal, which may be as small as 1,000th of the diameter of a proton. To combat this, scientists employ cryogenic cooling and materials with ultra-low thermal noise, such as fused silica. Even the choice of mirror coatings is critical. Some designs aim to minimize absorption of light, which reduces heat generation, and in turn thermal noise. Perhaps most enigmatic is quantum noise, a fundamental limit imposed by the laws of physics. According to Heisenberg's uncertainty principle, there is an inherent randomness to the behavior of photons, the particles of light used to measure spacetime distortions. In a gravitational wave detector, this manifests as shot noise fluctuations in the number of photons arriving at the photodetector and radiation pressure noise, where the momentum of photons pushes the mirrors ever so slightly. These quantum effects become particularly pronounced at high frequencies, where the energy of individual photons plays a dominant role. To suppress this noise, advanced interferometers utilize techniques like squeezed light, which manipulates the quantum properties of light to reduce uncertainty in specific measurements. By squeezing the noise in one property, such as phase, scientists can amplify the sensitivity in another, such as amplitude, effectively sharpening the detector's ear for the faintest cosmic whispers. Once the noise is minimized, the next step is to extract meaningful signals from the data. This is where algorithms and computational power come into play. One of the most powerful tools in this arsenal is matched filtering, a method akin to listening for a specific melody in a crowded room. Scientists generate theoretical waveforms representing the gravitational waves produced by astrophysical events, such as the inspiral and merger of two black holes. These waveforms are derived from Einstein's equations of general relativity and numerical simulations of extreme cosmic phenomena. By comparing the incoming data to these templates, algorithms can identify potential matches. The process is computationally intensive, requiring supercomputers to scan through millions of possible waveforms, each differing slightly in parameters like mass, spin, and orbital orientation. A true signal emerges not as a single peak, but as a coherent pattern that aligns with multiple templates, a statistical fingerprint that distinguishes it from random noise. However, the journey from data to discovery is fraught with caution. False positives are an ever-present threat, arising from glitches in the instrument, software errors, or even cosmic coincidences. To guard against this, scientists subject candidate signals to rigorous vetting. One method involves injecting simulated signals into the data stream without informing the analysts, a practice known as blind injections. When a team successfully detects such a signal, it validates the robustness of their analysis pipeline. Conversely, when a candidate signal fails to hold up under scrutiny, it serves as a reminder of the universe's deceptive complexity. The process is as much about skepticism as it is about discovery, a delicate balance between open-minded curiosity and methodical verification. Through this intricate dance of hardware and software, noise becomes not an obstacle, but a canvas upon which the universe reveals its secrets. Each detected gravitational wave is a testament to humanity's ability to listen beyond the immediate, to hear the echoes of cataclysms that occurred eons ago, and whose light has yet to reach us. The detection of gravitational waves marks more than a technological triumph. It heralds a paradigm shift in astronomy. For centuries, our understanding of the cosmos has been filtered through the lens of electromagnetic radiation, visible light, radio waves, X-rays, and gamma rays. These messengers have illuminated the life cycles of stars, the structure of galaxies, and the remnants of ancient supernovae. Yet many cosmic phenomena remain invisible to these traditional eyes. Black holes, for instance, do not emit light. Their presence is inferred only through their gravitational influence on surrounding matter. Gravitational waves, however, offer a direct view into these dark realms. When two black holes spiral toward each other, they radiate energy in the form of ripples in spacetime, a process that culminates in a violent merger. These events, once theoretical, now appear in our data as fleeting but unmistakable signals, chirps that rise in frequency and amplitude before fading into silence. Such discoveries have redefined our understanding of the universe, revealing a population of stellar mass black holes with masses far greater than previously thought and confirming the existence of binary black hole systems. Beyond black holes, gravitational waves have opened windows into the lives of neutron stars, the dense remnants of supernova explosions. When these hyperdense objects collide, they unleash not only gravitational waves, but also electromagnetic counterparts, Kilonova and short gamma-ray bursts, that provide a wealth of information about heavy element formation and the expansion rate of the universe. By combining gravitational wave data with observations from telescopes across the electromagnetic spectrum, scientists have entered an era of multi-messenger astronomy, where different types of cosmic signals converge to paint a fuller picture of the universe. This synergy has already yielded groundbreaking results, such as the 2017 observation of a neutron star merger that confirmed the origin of gold and platinum in the cosmos. Yet, for all its promise, gravitational wave astronomy is a discipline defined by fragility. Each detection is a fleeting moment, a signal that arrives after traversing billions of years of space and time, only to be buried in the noise of our own planet. The process of extracting these signals is akin to assembling a puzzle with missing pieces, where every assumption carries the risk of error. Theoretical models must be precise, observational biases must be accounted for, and the very act of measurement introduces uncertainties that ripple through the analysis. This vulnerability underscores a profound truth. Knowledge is not a fixed edifice but a dynamic construct, constantly refined by new evidence and the relentless pursuit of accuracy. The fragility of our understanding is not a weakness but a feature of the scientific enterprise, one that compels us to remain humble in the face of the unknown. Moreover, the quest to decode the cosmic symphony reflects a deeper philosophical tension between order and entropy. The universe, governed by the second law of thermodynamics, is inexorably drifting toward a state of maximum disorder. Yet, within this grand entropy, pockets of order emerge. Planets orbiting stars, galaxies forming intricate clusters, and gravitational waves carrying the imprints of cosmic collisions. The act of detecting these waves is in a sense a defiance of entropy, a reaching into the void to recover patterns that might otherwise be lost. It is a reminder that while the universe may be heading toward uniformity, the human mind seeks to carve meaning from the chaos, to find harmony in the dissonance. This pursuit is not without cost. The resources required to build and operate gravitational wave detectors, millions of dollars, decades of research, and the collective efforts of thousands of scientists are a testament to the value we place on understanding our place in the cosmos. And yet, for every signal detected, there are countless others that remain elusive, hidden in the noise or beyond the reach of current technology. The gaps in our knowledge are as instructive as the discoveries themselves, guiding future innovations and deepening our appreciation for the mysteries that lie ahead. In this way, gravitational wave astronomy is both a celebration of human ingenuity and a humbling acknowledgement of the limits of our perception. It reminds us that the universe is not a static entity to be catalogued, but a living, evolving story in which we are both participants and observers. The symphony we strive to decode is not merely a record of past events, but a dialogue between the cosmos and ourselves, a conversation that continues to unfold with each new signal detected and each new question raised. To refine the search for gravitational waves, scientists have turned to a tool as ancient as imagination and as modern as artificial intelligence: simulation. Just as composers rehearse symphonies before a performance, researchers generate synthetic data to anticipate the universe's most elusive notes. These simulations are not mere guesses, but meticulous reconstructions of astrophysical phenomena, grounded in the equations of general relativity and the latest observational data. By modeling the in-spiral, merger and ringdown of binary black holes, or the violent collisions of neutron stars, scientists create a library of theoretical waveforms that serve as templates for matched filtering. Each simulation is a virtual echo of the cosmos, a prediction of what the universe might sound like if we could hear it. But simulations do more than prepare detectors for the unknown. They reveal the boundaries of our understanding. When a simulated waveform diverges from observed data, it signals a gap in our models, perhaps an overlooked nuance of space-time dynamics or an unaccounted-for astrophysical process. These discrepancies drive innovation, prompting researchers to revisit assumptions and refine theories. Moreover, simulations allow scientists to test the limits of their instruments, identifying sources of noise or systematic errors that might otherwise go unnoticed. In this way, the interplay between theory and observation becomes a feedback loop, each iteration sharpening the focus of our cosmic vision. As the field of gravitational wave astronomy advances, simulations will play an increasingly vital role in unlocking the universe's deepest secrets. They will guide the design of next-generation detectors, optimize data analysis techniques, and even predict phenomena yet to be discovered. The next segment will delve into the art of simulation itself, exploring how scientists conjure virtual universes to illuminate the real one. For now, suffice it to say that in the quest to decode the cosmic symphony, simulations are not just tools, they are the unsung melodies that help us tune our instruments to the universe's true song. Long before the first ripples of space-time reach Earth, before the faint hum of gravitational waves brushes against the most sensitive instruments on our planet, there exists a realm where these cosmic whispers are born. Not in the void of space, but in the labyrinthine circuits of supercomputers. These machines, often dismissed as mere tools of calculation, are in fact time machines of a different kind. They do not transport us through the fabric of the universe in the way a DeLorean might, but they do something far more profound. They resurrect the past, reconstructing the violent births of black hole mergers, the death throes of neutron star collisions, and the silent symphonies of warped geometry. With equations so intricate they seem plucked from the mind of a god, supercomputers simulate events so distant and extreme that even light cannot convey their story in time. By modeling these phenomena, they allow humanity to peer into the universe's most inaccessible corners, to hear what would otherwise remain unheard, and to see what would otherwise remain unseen. The stakes of these simulations are staggering. When two black holes spiral toward each other in the final moments of their existence, they do not merely collide, they dance. Their gravitational fields warp space-time itself, sending out concentric waves that ripple across the cosmos at the speed of light. These waves, though invisible to telescopes, carry an immense amount of information: the masses of the black holes, their spins, the orientation of their orbits, and the energy released in their cataclysmic union. Yet detecting these waves is no simple task. Gravitational wave observatories like LIGO and Virgo operate by measuring minute distortions in spacetime, distortions so small that they correspond to changes in distance, smaller than the width of a proton. Without a reference point, these detections would be akin to trying to decipher a language without any prior knowledge of its grammar. This is where supercomputers step in. By solving Einstein's equations for colliding black holes, they generate theoretical waveforms that act as blueprints for what the universe should sound like in the moments of such cosmic violence. These simulations are not just predictions, they are the scaffolding upon which the entire field of gravitational wave astronomy is built. Projects like the Simulating Extreme Spacetimes (SXS) initiative exemplify the marriage of computational power and theoretical physics. SXS pioneers the use of numerical relativity, a branch of physics that grapples with Einstein's equations in their full, non-linear glory. These equations, formulated over a century ago, describe gravity not as a force, but as the curvature of spacetime caused by mass and energy. However, when applied to dynamic systems like colliding black holes, they become a mathematical monster, so complex that even the brightest minds of the 20th century could not solve them analytically. It took the advent of supercomputers to crack this code, transforming abstract mathematics into tangible simulations. The result is a library of waveforms, each representing a unique cosmic event that serve as a Rosetta Stone for decoding the universe's hidden messages. This interplay between simulation and observation is the heartbeat of modern astrophysics. It is a dance between the known and the unknown, where supercomputers act as both artists and scientists, painting visions of the universe that have yet to be witnessed. And yet, the true marvel lies not in the simulations themselves, but in what they enable, the ability to listen to the universe in a way that was once thought impossible. Through these digital time machines, we are granted a rare privilege to witness the birth of spacetime's ripples before they arrive, to understand the music of the cosmos before it is heard, and to glimpse the universe's secrets long before they reach our shores. At the heart of gravitational wave simulations lies the art of numerical relativity, a discipline that transforms Einstein's equations into a computational ballet. These equations, elegant in their abstraction, describe how mass and energy curve spacetime, and how that curvature in turn dictates the motion of objects within it. Yet when applied to the dynamic, high-energy environments of colliding black holes or neutron stars, they become a system of partial differential equations so complex that their solutions defy analytical methods. Numerical relativity steps in as the universe's interpreter, translating these equations into algorithms that can be solved iteratively on supercomputers. The process is akin to solving a multi-dimensional chess game, where every move alters the rules of the board itself. The foundation of numerical relativity is rooted in discretization, the division of continuous spacetime into a grid of points, each representing a snapshot of the system at a given moment. Supercomputers then calculate how these points evolve over time, using finite difference methods to approximate derivatives and integrate the equations forward in minuscule time steps. This requires immense computational power, as the simulations must resolve not only the massive scales of black holes, but also the subatomic level distortions of spacetime near their event horizons. For instance, a typical simulation of two merging black holes might involve billions of grid points and millions of iterations, each demanding precise calculations to avoid numerical instabilities that could render the results meaningless. One of the greatest challenges in these simulations is handling the singularities inherent in black holes. A black hole's singularity, a point of infinite density, where the laws of physics as we know them break down, is a mathematical nightmare for numerical relativity. To circumvent this, researchers employ techniques like excision, where the region inside the event horizon is simply removed from the computational domain. This allows the simulation to focus on the observable dynamics outside the black hole, where gravitational waves are generated. Another innovation is the use of adaptive mesh refinement, which dynamically adjusts the resolution of the grid to concentrate computational resources where they are needed most, such as near the merging black holes, or in regions of strong curvature. The output of these simulations is a waveform, a graphical representation of the gravitational wave signal emitted during a cosmic event. These waveforms are not static. They evolve in time, capturing the in-spiral, merger, and ring-down phases of a black hole collision. During the in-spiral phase, the two black holes orbit each other, gradually losing energy through gravitational radiation and spiraling closer. The waveform during this period is characterized by increasing frequency and amplitude, much like the rising pitch and volume of a siren. As the black holes merge, the waveform reaches a peak, followed by a rapid oscillation, as the newly formed black hole settles into a stable configuration, a process known as ring-down. Each stage of this sequence is encoded in the simulated waveform, allowing researchers to extract critical parameters such as the masses and spins of the black holes. These waveforms form the backbone of gravitational wave data analysis. When an observatory detects a signal, it compares the observed waveform to a catalog of theoretical templates generated by simulations. This process, known as matched filtering, relies on the principle that the best matching template corresponds to the most likely physical scenario. For example, the 2015 detection of GW 150914, the first direct observation of gravitational waves, was made possible by comparing the signal to a pre-computed waveform for two black holes of approximately 36 and 29 solar masses. The precision of these matches is astonishing. The observed signal aligned with the simulated waveform to within a fraction of a millisecond, confirming not only the existence of gravitational waves, but also the accuracy of numerical relativity. The development of these simulations is a testament to interdisciplinary collaboration. Physicists work alongside computer scientists to optimize algorithms, Mathematicians refine the underlying equations, and engineers design the hardware capable of handling the computations. Projects like SXS have been instrumental in advancing this field, producing open-access waveform libraries that serve as gold standards for the gravitational wave community. These libraries are not static. They are continually updated as new physical models are incorporated, such as the effects of magnetic fields in neutron star mergers, or the influence of environmental factors like surrounding gas clouds. Yet, despite their sophistication, numerical relativity simulations are not infallible. They rely on approximations and assumptions, such as the choice of coordinate systems or the treatment of matter in neutron stars. Researchers are constantly refining these models to reduce uncertainties, ensuring that the theoretical waveforms remain as accurate as possible. This iterative process mirrors the scientific method itself, a cycle of hypothesis, computation, validation, and refinement that drives our understanding of the universe ever forward. In essence, numerical relativity is the bridge between the abstract mathematics of general relativity and the tangible reality of gravitational wave observations. It is a field where the boundaries between theory and experiment blur, where equations become simulations, and where simulations become the lens through which we interpret the universe. Through this lens, we gain not only a deeper understanding of black holes and neutron stars, but also a profound appreciation for the computational ingenuity required to unravel the mysteries of space-time. Gravitational wave simulations are more than just tools for interpreting observations. They are laboratories for testing the very foundations of physics. In the extreme environments modeled by numerical relativity, where space-time is warped to its breaking point and gravity dominates all other forces, the predictions of Einstein's theory of general relativity are put to the ultimate test. These simulations allow scientists to explore scenarios that are impossible to replicate in terrestrial experiments, offering a unique opportunity to probe the limits of our understanding. For instance, when two black holes merge, the resulting space-time distortion is so intense that it creates a region where gravity is stronger than anything observed in the universe. In such a regime, general relativity predicts phenomena like the emission of gravitational waves with specific frequencies and amplitudes, but it is also a realm where the theory may falter. By comparing simulated waveforms to observed signals, researchers can search for deviations that might hint at new physics beyond Einstein's framework. One of the most striking implications of these simulations is their ability to confirm or challenge the validity of general relativity in the strong field regime. While the theory has passed every experimental test to date, from the bending of starlight during solar eclipses to the precise orbit of Mercury, its behavior in the vicinity of black holes remains uncharted territory. Gravitational wave simulations provide a way to map this terrain. For example, the 2017 detection of GW17817, a binary neutron star merger, offered a rare opportunity to study gravity in the presence of matter, not just in the vacuum of space-time. The waveform of this event closely matched the predictions of numerical relativity, reinforcing confidence in the theory. However, subtle discrepancies, if any, could signal the need for modifications. Some alternative theories of gravity, such as scalar tensor theories or modified Newtonian dynamics, MOND, predict different behaviors in strong gravitational fields. By running simulations under these alternative frameworks, researchers can compare their predictions to observational data, potentially uncovering cracks in the edifice of general relativity. Beyond validating existing theories, gravitational wave simulations also open the door to discovering entirely new phenomena. For instance, the ring-down phase of a black hole merger, the moment when the final black hole settles into equilibrium, is governed by the no-hair theorem, which states that black holes can be fully described by their mass, spin, and electric charge. If this theorem holds true, the ring-down waveform should exhibit a specific pattern of damped oscillations. However, if the observed signal deviates from this pattern, it could indicate the presence of exotic structures like hairy black holes or remnants of quantum gravity effects. Such discoveries would revolutionize our understanding of the universe, bridging the gap between general relativity and quantum mechanics. Moreover, these simulations are reshaping our understanding of the cosmos on a larger scale. By analyzing the population of gravitational wave sources detected by observatories, Researchers can infer the rates and distributions of cosmic events like black hole mergers and neutron star collisions. These insights contribute to our knowledge of stellar evolution, galaxy formation, and the history of the universe itself. For example, the unexpectedly high masses of some observed black holes suggest that they may have formed through different mechanisms than previously thought, such as hierarchical mergers in dense stellar clusters. Simulations help disentangle these possibilities, providing a statistical framework for interpreting the data. The implications of gravitational wave simulations extend beyond astrophysics into the realm of cosmology. By studying the stochastic gravitational wave background, the cumulative hum of all unresolved gravitational wave sources in the universe, scientists hope to probe the early universe, including the epoch of inflation. This hypothetical period of exponential expansion, proposed to explain the uniformity of the cosmic microwave background, is expected to have produced gravitational waves. Detecting these primordial ripples would offer a direct window into the universe's infancy, complementing observations of the cosmic microwave background and large-scale structure. While current detectors are not yet sensitive enough to observe this background, future observatories like the Laser Interferometer Space Antenna LISA may one day make it possible. In the meantime, simulations help model what this background might look like, guiding the development of detection strategies. Perhaps the most profound implication of gravitational wave simulations is their role in redefining humanity's place in the universe. For centuries, we have relied on light to observe the cosmos, but gravitational waves offer a new way of seeing, one that transcends the limitations of electromagnetic radiation. Unlike light, which can be absorbed, scattered, or blocked by intervening matter, gravitational waves pass unimpeded through the universe, carrying information from the most extreme environments. This means that events occurring in the depths of intergalactic space, shielded by thick veils of dust or hidden behind the event horizons of black holes, can still leave their mark on spacetime. By decoding these marks, we are not merely observing the universe, we are listening to it, feeling its vibrations and participating in its grand unfolding story. Yet, for all their power, gravitational wave simulations also remind us of the vastness of what remains unknown. The equations of numerical relativity are built on the assumption that spacetime is a smooth, continuous fabric, but quantum gravity theories suggest that at the smallest scales, spacetime may be discrete or subject to fluctuations. Current simulations cannot resolve these quantum effects, as they require energies and resolutions far beyond our technological capabilities. However, they lay the groundwork for future breakthroughs, providing a scaffold upon which new theories can be tested and refined. In this sense, gravitational wave simulations are not just tools for discovery, they are seeds for the next generation of scientific inquiry, waiting to grow into revelations that we cannot yet imagine. As we stand on the precipice of a new era in gravitational wave astronomy, the simulations that have guided us thus far are only the beginning. The current generation of detectors, though revolutionary, operates at the edge of their sensitivity, constrained by technological limitations and the noise of our own planet. Yet the universe has much more to say, and our tools must evolve to hear it. Future observatories, both on Earth and in space, promise to expand our cosmic hearing, capturing ripples from the most distant and enigmatic events in the universe. Instruments like the Laser Interferometer Space Antenna, LISA, slated for launch in the 2030s, will detect gravitational waves at lower frequencies, opening a window into the mergers of supermassive black holes and the inspirals of compact binaries in the galactic center. Meanwhile, ground-based detectors are undergoing upgrades to enhance their sensitivity, allowing them to probe deeper into the cosmos and detect signals from the earliest epochs of the universe. But these advancements will demand more than improved hardware. They will require ever more sophisticated simulations. As the range of detectable sources expands, so too will the complexity of the waveforms we must predict. The next frontier of gravitational wave astronomy will involve deciphering signals from sources we have yet to imagine, from the violent collisions of neutron stars in the aftermath of supernovae, to the elusive echoes of cosmic strings from the early universe. To meet this challenge, Supercomputers will need to push the boundaries of numerical relativity, incorporating new physical models and tackling problems once deemed intractable. In doing so, they will continue their role as time machines, not only reconstructing the past, but also shaping the future of our understanding. For now, as we listen to the universe through the lens of gravitational waves, we are reminded of the delicate balance between the known and the unknown. Every simulation, every detected signal, brings us closer to unraveling the mysteries of space-time. Yet each discovery also reveals new questions. The journey is far from over. The cosmos, vast and inscrutable, waits patiently for us to improve our instruments, refine our theories, and expand our vision. And in that waiting, it offers a promise that the more we learn, the more we realize how much remains to be discovered. In the vast expanse of the cosmos, where light from distant stars takes eons to reach our eyes, the universe speaks in ways far beyond the visible spectrum. For decades, humanity has strained to decipher these messages, relying on telescopes tuned to electromagnetic waves, radio, infrared, optical, X-ray and gamma. Yet these tools capture only fragments of the story. They are akin to listening to a symphony through a single instrument, missing the harmonies and rhythms that define its essence. Enter gravitational waves, the ripples in space-time itself. Born from cataclysmic cosmic events, these ripples, first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, have opened a new window to the universe. But even LIGO and its counterparts on Earth have limitations. Their sensitivity is constrained by seismic noise, atmospheric disturbances, and the very physics of their terrestrial foundations. They can hear the high-pitched squeals of binary neutron star mergers, but the deeper, more resonant tones, the low-frequency hums of supermassive black hole collisions elude them. To truly understand the universe's most profound phenomena, we must venture beyond Earth into the silent vacuum of space, where future observatories like the Laser Interferometer Space Antenna LISA will attune themselves to the deepest bass notes of the cosmos. This journey marks the next chapter in humanity's quest to comprehend the universe, expanding our cosmic hearing to the faintest echoes of its most ancient and powerful events. The concept of LISA represents a leap in both engineering and imagination. Scheduled for launch in the 2030s, this space-based observatory will consist of 3 identical spacecraft arranged in an equilateral triangle, with each side stretching approximately 2.5 million kilometers, roughly 6 times the distance between Earth and the Moon. These spacecraft will orbit the Sun in a triangular formation, trailing Earth in its path, forming a vast interferometric detector suspended in the void. At the heart of LISA's design lies the principle of laser interferometry, a technique refined by ground-based detectors like LIGO and Virgo. However, LISA's spatial configuration transforms this method into something unprecedented. Instead of relying on kilometer-scale arms etched into the Earth's crust, LISA's arms are millions of kilometers long, allowing it to measure minute distortions in spacetime caused by gravitational waves at frequencies far below those detectable by terrestrial instruments. The key to LISA's sensitivity lies in its ability to isolate the spacecraft from external disturbances. Each spacecraft houses free-floating gold-platinum test masses, shielded within vacuum chambers to protect them from stray forces. Lasers beam between the spacecraft, measuring the distance between the test masses with extraordinary precision, down to picometers, a fraction of the diameter of an atom. When a gravitational wave passes through the system, it subtly stretches and compresses the distances between the test masses, altering the interference pattern of the lasers. By analyzing these shifts, LISA will detect the gravitational signatures of events such as the mergers of supermassive black holes, whose combined masses can reach billions of times that of the Sun. These mergers, occurring at the hearts of galaxies during galactic collisions, emit gravitational waves with frequencies in the millihertz range, waves too slow and too weak for ground-based detectors to perceive. Complementing LISA's spacefaring ambitions, advancements in terrestrial observatories like the Einstein telescope are pushing the boundaries of detection. This proposed underground observatory, designed to operate in the 2040s, will feature a triangular array of 3 interferometers, each with 10-kilometer-long arms, cooled to near absolute zero to minimize thermal noise. Its innovative design, incorporating cryogenic materials and advanced seismic isolation systems, aims to achieve a sensitivity 10 times greater than current detectors. Together, these instruments form a multi-messenger approach to astronomy, combining gravitational wave data with electromagnetic observations to paint a fuller picture of the universe. While LISA will probe the low-frequency regime, the Einstein telescope will refine our understanding of higher frequency sources, such as neutron star binaries and supernovae. This synergy between space and ground-based observatories ensures that no cosmic phenomenon escapes our attention, bridging the gap between the faintest whispers and the most violent roars of the universe. The implications of these next-generation detectors extend far beyond the study of black holes. By tuning into the low-frequency gravitational waves they will capture, we may uncover phenomena that have long remained hidden in the shadows of astrophysical theory. One such possibility lies in the detection of cosmic strings, hypothetical one-dimensional defects in spacetime, relics of the universe's earliest moments. These structures, if they exist, would have formed during phase transitions in the hot, dense plasma of the early universe, analogous to cracks forming in cooling metal. As cosmic strings vibrate and interact, they could emit gravitational waves at specific frequencies, leaving a telltale signature in LISA's data. Such a discovery would not only confirm a key prediction of grand unified theories, but also provide a direct window into the conditions of the universe mere fractions of a second after the Big Bang. Another tantalizing prospect is the search for primordial black holes, hypothetical objects that may have formed in the first moments of the universe before the first stars ignited. Unlike stellar mass black holes, which collapse from dying stars, primordial black holes could span a wide range of masses, from microscopic to hundreds of solar masses, and serve as viable candidates for dark matter. By analyzing the distribution and frequency of gravitational wave events, LISA and its successors could determine whether these enigmatic objects populate the cosmos in sufficient numbers to account for the unseen mass that binds galaxies together. If detected, primordial black holes would revolutionize our understanding of dark matter and the universe's evolutionary history. Perhaps the most audacious implication of next-generation gravitational wave detectors lies in their potential to probe the multiverse, a theoretical framework suggesting that our universe is but one of countless others, each existing in separate dimensions or regions of space-time. Within certain models of string theory and inflationary cosmology, collisions between parallel universes could generate gravitational waves at frequencies detectable by LISA. These waves, imprinted with the geometry and dynamics of a higher dimensional reality, would offer an unprecedented glimpse into realms beyond our observable universe. While such ideas remain speculative, the ability to test them empirically transforms philosophy into science, grounding abstract concepts in measurable phenomena. Even within the confines of known physics, the data gathered by these instruments will deepen our understanding of fundamental forces and space-time itself. For instance, the precise timing of gravitational wave signals from supermassive black hole mergers could test Einstein's general theory of relativity under extreme conditions, potentially revealing deviations that hint at quantum gravity or alternative theories of gravity. Additionally, the study of gravitational lensing effects, where the curvature of spacetime bends and amplifies gravitational waves, could map the distribution of matter in the universe with unparalleled accuracy. Each signal detected by LISA or the Einstein telescope will be a thread in a vast tapestry, weaving together the stories of cosmic collisions, the birth of galaxies, and the hidden architecture of existence. As we prepare to listen more deeply to the universe's gravitational symphony, we are poised to confront questions that transcend the present moment. The next generation detectors are not merely tools for cataloging cosmic events. They are instruments of revelation, capable of reshaping our understanding of the universe's origins, its evolution, and its ultimate fate. The gravitational waves they capture will carry secrets encoded in the fabric of space-time itself, offering clues about the forces that govern the cosmos on scales both unimaginably vast and infinitesimally small. Yet, for all their promise, these instruments also raise profound uncertainties. Will the signals we detect conform to the elegant equations of general relativity, or will they expose the fractures in our current models, demanding a radical reimagining of physics? And as we trace the mergers of supermassive black holes across billions of light-years, what do these events tell us about the destiny of galaxies, the expansion of the universe, and the inexorable march toward entropy? These questions lead us to the next frontier of exploration, the fate of the universe. As gravitational wave astronomy matures, it will intersect with studies of dark energy, the mysterious force driving the accelerated expansion of the cosmos. By analyzing the redshift of gravitational wave sources, scientists hope to measure the rate of cosmic expansion with unprecedented precision, potentially resolving the current tension between different methods of determining the Hubble constant. Moreover, the interplay between gravitational waves and electromagnetic observations, what astronomers call multi-messenger astronomy, will allow us to track the life cycles of massive objects, from their formation in the early universe to their eventual decay in the far future. Whether the universe ends in a big freeze, a big rip, or some yet undiscovered scenario, gravitational wave detectors will help us chart the final movements of this cosmic dance. Yet, for all their technological sophistication, these instruments remind us of our humble position in the cosmos. They are human creations, born of ingenuity and curiosity, yet they reach out to touch the very threads of space-time, translating the universe's silent vibrations into data we can comprehend. In this way, next-generation detectors embody the paradox of scientific exploration. The more we learn, the more we realize how much remains unknown. As LISA and its successors begin their celestial listening, they will not only expand our cosmic hearing, but also deepen our reverence for the mysteries that lie ahead. The universe, in all its vastness and complexity, continues to beckon, inviting us to listen, to wonder, and to imagine. In the grand theater of the cosmos, gravitational waves emerge as silent messengers, carrying whispers from the most violent and enigmatic events in the universe. These ripples, born from the collisions of massive celestial bodies, such as black holes and neutron stars, propagate through the very fabric of space-time, stretching and compressing reality in ways imperceptible to the human senses. Yet these imperceptible distortions hold profound significance. They are not merely echoes of the past, but potential keys to unlocking the universe's ultimate fate. As scientists strain to detect these faint disturbances, they are not only peering into the distant past, but also glimpsing the possibilities of what lies ahead. Will the universe continue expanding indefinitely, its galaxies drifting farther apart until all light fades into darkness? Or will gravity ultimately triumph, drawing everything back together in a cosmic collapse, a reverse of the Big Bang itself? And could the mysterious force of dark energy, which drives the accelerated expansion of the universe, one day become so powerful that it tears apart even the fundamental structures of matter, ushering in a cataclysmic Big Rip? These questions, though daunting in their scope, are not beyond the reach of human inquiry. Gravitational waves, detected through advanced observatories like LIGO and Virgo, offer a unique window into the universe's most extreme phenomena. Unlike light, which can be absorbed or scattered by intervening matter, gravitational waves travel unimpeded across billions of light years, preserving the raw information of their origins. In this way, they serve as pristine records of cosmic history, carrying imprints of the moments when stars were born, died, and collided in fiery spectacles. By studying these ripples, astrophysicists can not only reconstruct the events that generated them, but also refine their understanding of the universe's expansion rate, the Hubble constant, which is crucial for predicting its ultimate destiny. Moreover, gravitational waves may yet reveal the nature of dark energy, an enigmatic force that defies conventional physics and governs the universe's accelerating expansion. If future detections uncover subtle variations in the properties of these ripples, they could provide invaluable clues about whether the universe will endure in an endless expansion or succumb to a final, irreversible unraveling. Beyond the scientific implications, the study of gravitational waves evokes a sense of awe and humility. They remind us that we are part of a vast, dynamic cosmos, in which time and space are not fixed but ever shifting. The very act of detecting these ripples is akin to listening to the heartbeat of the universe, a rhythm that has been playing since the earliest moments of existence. As we continue to refine our instruments and expand our observational capabilities, we edge closer to deciphering the cosmic symphony, a symphony that may one day reveal the ultimate fate of all that is. At the heart of the universe's fate lies the Hubble constant, a fundamental parameter that quantifies the rate at which the cosmos is expanding. This value, often denoted as h0, is crucial for determining the age of the universe and predicting its long-term evolution. However, despite decades of research, there remains a persistent discrepancy between different methods of measuring the Hubble constant. Observations of the cosmic microwave background radiation suggest one value, while measurements of distant supernovae and galaxy redshifts indicate another. Resolving this tension is essential for understanding whether the universe will continue to expand indefinitely, eventually slow down and collapse under its own gravity, or accelerate toward a catastrophic Big Rip. Here, gravitational waves offer a novel approach, one that bypasses many of the uncertainties inherent in traditional methods. When two massive objects, such as neutron stars or black holes, spiral toward each other and collide, they emit gravitational waves that ripple through space-time. These ripples carry with them precise information about the distance to the event, independent of the usual assumptions required for optical observations. By combining this distance measurement with the observed redshift of the host galaxy, scientists can calculate the Hubble constant with remarkable precision. This method, known as using gravitational wave standard sirens, provides a direct and independent means of measuring the universe's expansion rate. With each new detection, researchers refine their estimates of h0, gradually narrowing the gap between conflicting results and bringing us closer to a definitive answer about the universe's ultimate fate. Moreover, gravitational waves may shed light on the nature of dark energy, the mysterious force driving the universe's accelerated expansion. While general relativity describes gravity as a curvature of space-time, it does not account for the repulsive force exerted by dark energy. Understanding its true nature is one of the greatest challenges in modern cosmology. Some theories suggest that dark energy is a property of space itself, an intrinsic energy density that remains constant over time. Others propose that it is a dynamic field, evolving as the universe expands. Gravitational wave observations may help distinguish between these possibilities by revealing subtle changes in the expansion rate over cosmic time. For instance, if dark energy is not constant but instead increases in strength, it could lead to a Big Rip scenario, in which the universe tears itself apart at an ever-accelerating pace. Detecting such a deviation would not only validate or refute current theoretical models, but also reshape our understanding of the fundamental laws governing the cosmos. Beyond the immediate implications for the Hubble constant and dark energy, gravitational waves have the potential to uncover primordial ripples left over from the earliest moments of the universe. During the brief instant of cosmic inflation, a period of exponential expansion in the first fraction of a second after the Big Bang, gravitational waves may have been imprinted on the fabric of space-time. Detecting these ancient ripples would provide direct evidence of inflation and offer insight into the conditions that shape the universe's structure. Current ground-based detectors, such as LIGO and Virgo, are not sensitive enough to observe these primordial waves, but future observatories, including space-based interferometers like the Laser Interferometer Space Antenna LISA, may be capable of probing this cosmic echo. Such a discovery would not only confirm a key prediction of the inflationary model, but also open a new window into the universe's earliest history, allowing us to peer further back in time than ever before. As our ability to detect and analyze gravitational waves continues to improve, so too does our capacity to address some of the most profound questions in cosmology. These ripples in space-time, once thought to be mere theoretical curiosities, have now become tangible tools for exploring the universe's expansion, its mysterious dark energy, and perhaps even the events that transpired in the first moments of creation. Each detection brings us one step closer to understanding not only how the universe came to be, but also what awaits it in the distant future. The study of gravitational waves is more than a window into the universe's expansion. It is a bridge between the smallest scales of quantum mechanics and the vast, sweeping arcs of cosmic evolution. At the heart of this connection lies the tantalizing possibility that these ripples in spacetime may one day reveal the elusive framework of quantum gravity, the theory that seeks to unify Einstein's general relativity with the principles of quantum mechanics. While general relativity describes gravity as the curvature of spacetime caused by mass and energy, quantum mechanics governs the behavior of particles at the subatomic level. Despite decades of effort, physicists have yet to reconcile these two pillars of modern physics. However, gravitational waves may offer a rare opportunity to probe this unification. If quantum gravity indeed leaves imprints on the fabric of spacetime, then the most extreme cosmic events, such as the collision of black holes or the violent birth of the universe during inflation, could generate detectable signatures in the form of gravitational waves. By analyzing the subtle characteristics of these ripples, scientists may uncover deviations from classical predictions, offering clues about the quantum nature of gravity itself. One particularly intriguing avenue of exploration involves the search for cosmic strings, hypothetical one-dimensional defects in spacetime that may have formed in the early universe. These structures, predicted by certain extensions of particle physics and string theory, could vibrate and produce gravitational waves with distinct frequencies. If such waves are detected, they would provide direct evidence for the existence of cosmic strings and, by extension, support theoretical models that attempt to unify gravity with other fundamental forces. Moreover, these ripples could reveal insights into the energy scales at which quantum gravity becomes relevant, potentially shedding light on the conditions that existed in the first fractions of a second after the Big Bang. In this way, gravitational waves serve as a cosmic laboratory, allowing scientists to test theories that operate at energies far beyond what can be achieved in terrestrial particle accelerators. Yet, the implications of gravitational waves extend beyond the realm of theoretical physics. They also offer a profound perspective on the universe's ultimate fate, a fate that hinges on the interplay between gravity and dark energy. The current consensus among cosmologists is that the universe is not only expanding, but doing so at an accelerating rate, driven by dark energy. However, the precise nature of this mysterious force remains one of the greatest unsolved problems in science. Is it a static property of space itself, as suggested by Einstein's cosmological constant, or is it a dynamic field that evolves over time, as proposed by various quintessence models? The answer to this question will determine whether the universe will continue to expand indefinitely, eventually slowing down and collapsing in a cosmic contraction, or accelerating so rapidly that it tears apart galaxies, stars, and even individual atoms in a cataclysmic Big Rip. Gravitational waves may provide crucial evidence to resolve this uncertainty. By observing how the expansion rate of the universe influences the propagation of these ripples, scientists can infer the behavior of dark energy across cosmic time. If future observations reveal unexpected variations in the properties of gravitational waves, it could signal a departure from the standard model of cosmology and point toward a more complex, evolving form of dark energy. Furthermore, the study of gravitational waves underscores the deep interconnectedness of the cosmos. The same ripples that allow us to measure the Hubble constant and probe the nature of dark energy also originate from the most extreme environments in the universe, regions where gravity is so intense that it warps spacetime in ways that defy intuition. Black hole mergers, for instance, occur in regions of spacetime where quantum effects and gravitational forces dominate, making them ideal laboratories for testing the limits of our current understanding. Similarly, the mergers of neutron stars not only produce gravitational waves, but also emit electromagnetic radiation in the form of kilonovae, allowing astronomers to combine multiple forms of observation to build a more complete picture of cosmic events. These multi-messenger studies represent a new era in astronomy, one in which gravitational waves complement traditional observations in the visible spectrum, X-rays, gamma rays, and neutrinos. This interdisciplinary approach not only enhances our ability to interpret cosmic phenomena, but also reinforces the idea that the universe is a single, unified system governed by fundamental physical laws. As our understanding of gravitational waves continues to evolve, so too does our appreciation for the intricate tapestry of the cosmos. These ripples in spacetime are not merely passive echoes of the past. They are active participants in the unfolding story of the universe. From the quantum fluctuations that gave rise to the first structures in the cosmos, to the violent collisions of distant celestial bodies, gravitational waves encapsulate the full spectrum of cosmic history. In tracing their journey across the vast expanse of time and space, we are not only uncovering the mechanisms that shape the universe, but also confronting the profound mystery of our place within it. Are we mere observers, standing on the shores of an ever-expanding sea of knowledge, or are we in some fundamental way part of the cosmic symphony itself? As we continue to listen to the whispers of space-time, we may come to realize that the answers to these questions lie not only in the data we collect, but also in the way we perceive our relationship to the universe as a whole. As we stand at the precipice of these revelations, we are reminded that the pursuit of understanding the universe is not merely an intellectual endeavor, but a deeply human one. The gravitational waves that ripple through space-time are more than cosmic signals. They are echoes of the universe's most profound transformations, carrying within them the imprints of events that have shaped the cosmos since its inception. To detect these ripples is to listen to the heartbeat of the universe, to trace the pulse of a vast and intricate system that has evolved over billions of years. In this moment of scientific advancement, we are not only refining our knowledge of the cosmos, but also reaffirming our place within it. We are not isolated observers gazing upon an indifferent void. Rather, we are part of a continuous process of discovery, a species striving to comprehend the vast, shifting landscape of existence. The study of gravitational waves has already begun to redefine our understanding of the universe's origins and its eventual fate. It has revealed the dynamic nature of space-time, demonstrated the power of extreme cosmic events, and provided insights into the fundamental forces that govern reality. Yet, these discoveries are not just about numbers and equations. They are about perspective. They compel us to consider the grandeur of the cosmos and our role within it. As we refine our instruments and expand our observational horizons, we are not only gathering data, but also shaping our perception of the universe as a living, evolving entity. The next segment invites us to delve further into this cosmic narrative, to explore the profound implications of our discoveries, and to reflect on what it truly means to be a conscious presence within the unfolding story of the universe. Long before humans walked the Earth, long before the first galaxies coalesced from the primordial fireball, the universe was already composing itself. Every atom in your body, every carbon atom that forms the backbone of life, every oxygen molecule you inhale, every calcium in your bones, was born in the crucible of a dying star. These elements were not conjured from nothing. They were forged in the violent throes of stellar explosions, scattered across the void by the force of supernovae, and later gathered into planets, oceans, and living beings. You are not separate from this ancient process. You are its latest verse. When you look at your hands, you are gazing at the remnants of stars that burned billions of years ago, stars that lived and died to create the very substance of your existence. This is the profound truth of Stardust. We are not visitors to the cosmos, but its children, shaped by the same forces that sculpted the mountains, the rivers, and the spiral arms of galaxies. But the universe's connection to us runs even deeper than the atoms in our bodies. Consider the air you breathe, the nitrogen in your lungs, the iron in your blood. These elements were not only forged in the cores of stars, but also enriched by the cataclysmic collisions of neutron stars. Events so rare and energetic that they ripple the fabric of space-time itself. When two neutron stars spiral toward one another in a death embrace, they unleash gravitational waves, ripples in the cosmos, that travel for millions of years before reaching Earth. These waves are not just echoes of distant violence. They are messages, carrying stories of creation and destruction, of birth and rebirth. To detect them is to hear the universe humming in a frequency beyond human senses. A song written in the mathematics of relativity and the physics of quantum fields. And yet here we are, tiny creatures on a pale blue dot, capable of not only hearing these waves, but of decoding their meaning. We are not merely observers of the universe. We are participants in its grand symphony, woven into its rhythms by the same laws that govern the dance of galaxies. To understand this truth, is to feel the weight of humility and the swell of wonder. The atoms in our bodies, the gravitational waves that pass through us, the light from distant quasars, all of it is part of a single interconnected story. There is no boundary between the observer and the observed, no divide between the cosmos and ourselves. We are the universe contemplating itself, a fleeting but meaningful note in an eternal composition. As we embark on this journey through the concept of the cosmic orchestra, let us not only listen to the music, but also consider our place within it. What does it mean to be both a product of the stars and a seeker of their secrets? How does this realization reshape our understanding of who we are and where we come from? These questions will guide us as we delve into the symphony of the cosmos, where every vibration carries the pulse of existence itself. The universe is not silent. Though its vastness often feels empty, it is alive with vibrations, some visible in the form of light, others hidden in the fabric of space-time itself. Among the most profound of these are gravitational waves, ripples in the geometry of space and time predicted by Einstein's theory of general relativity over a century ago. These waves are not mere theoretical curiosities. They are the universe's way of speaking in a language older than atoms, older than stars. They are born in moments of cosmic upheaval, when massive objects accelerate through space-time. Their motion distorts the very structure of reality, sending out concentric waves like ripples in a pond. The most dramatic sources of these waves are the mergers of black holes and neutron stars, events so violent that they warp space-time on scales unimaginable to human intuition. Consider the collision of two black holes, each with the mass of dozens of suns. As they spiral inward, their immense gravity stretches and compresses the space around them, creating a gravitational wave that travels outward at the speed of light. By the time this wave reaches Earth, it has traversed millions or even billions of years of cosmic history, its energy diluted by the vastness of the universe. Yet despite its faintness, it still carries information about the moment of the merger, the masses of the black holes, their spins, the orientation of their orbits. Detectors like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo on Earth, and the future space-based LISA mission, have captured these whispers, allowing us to peer into the universe's most extreme phenomena. The first direct detection of gravitational waves in 2015, from the merger of two black holes 1.3 billion light-years away, marked a new era in astronomy. No longer confined to observing the universe solely through electromagnetic radiation, light, radio waves, X-rays, we now have a second sense, a way to hear the universe in a voice that transcends the limitations of sight. But gravitational waves are not just the product of recent cosmic events. They are also imprints of the universe's earliest moments. In the instant after the Big Bang, the universe expanded faster than light in a process called inflation, generating gravitational waves that left their mark on the cosmic microwave background, the afterglow of the infant universe. These primordial waves, though incredibly faint, could provide clues about the conditions that gave rise to galaxies, stars, and ultimately life. Their detection would confirm theories about the universe's origins and offer a glimpse into an epoch so far removed from our experience that it defies imagination. For now, such waves remain elusive, hiding in the noise of the cosmos. But the search continues, driven by the hope that we might one day decode the universe's first notes. What makes gravitational waves particularly remarkable is their ability to carry stories that other forms of radiation cannot. Light can be absorbed, scattered, or blocked by intervening matter, but gravitational waves pass through everything unimpeded. A wave from a neutron star merger 100 million light-years away would have traveled undisturbed by dust clouds, gas clouds, or even the supermassive black hole at the center of our galaxy. This means that gravitational waves offer a unique window into the universe's most obscured regions, including the mergers of black holes that do not emit light. By combining gravitational wave observations with traditional telescopes, astronomers have begun to unravel the mysteries of Kilonova, explosions powered by the fusion of heavy elements during neutron star collisions. These events are not only spectacular displays of cosmic violence, but also the birthplaces of gold, platinum, and other heavy elements that enrich the universe. Without gravitational waves, much of this story would remain untold. Yet for all their power, gravitational waves are subtle. The distortions they cause in space are so minuscule that they require instruments capable of measuring changes smaller than the width of a proton. This precision is achieved through interferometers, which split laser beams and send them down perpendicular arms several kilometers long. When a gravitational wave passes through, it stretches one arm while compressing the other, altering the interference pattern of the recombined beams. The sensitivity required to detect such tiny shifts is staggering, equivalent to measuring the distance to the nearest star with a precision of less than the diameter of a hydrogen atom. Achieving this level of precision demands cutting-edge technology, from ultra-stable lasers to seismic isolation systems that shield detectors from terrestrial vibrations. The success of these efforts is a testament to human ingenuity, a reminder that our curiosity drives us to push the boundaries of what is possible. As we listen to the universe through gravitational waves, we are not merely passive recipients of knowledge, we are active participants in a dialogue that spans eons. Each detected signal is a conversation between our instruments and the cosmos, a moment of connection between the present and the distant past. When LIGO scientists analyzed the data from GW 150914, the first direct observation of gravitational waves, they were not just analyzing numbers, they were translating the universe's ancient language into something we could understand. In doing so, they bridged the gap between the abstract equations of physics and the tangible reality of human experience. This act of interpretation is both scientific and poetic, a recognition that the universe speaks in patterns, and we are learning to read them. The study of gravitational waves also underscores the interconnectedness of cosmic phenomena. Black hole mergers, neutron-star collisions, and the Big Bang are not isolated events. They are threads in the tapestry of the universe's evolution. The elements forged in these events are the building blocks of planets, the fuel for stars, and the raw materials for life. The gravitational waves they produce are the echoes of this evolutionary dance, a record of how the universe has transformed over 13.8 billion years. To study these waves is to trace the lineage of matter and energy, to witness the universe's capacity for both destruction and creation. It is a reminder that the cosmos is not a static entity, but a dynamic, ever-changing symphony, where every note contributes to the harmony of existence. To recognize that we are composed of stardust and that gravitational waves resonate through our very being is to confront a truth that reshapes our understanding of identity and purpose. This realization dissolves the illusion of separateness that often defines human experience. When we gaze at the night sky, we are not simply looking at distant lights, we are peering into the origins of our own existence. The elements in our bodies, the gravitational waves that pass through us, and the cosmic microwave background that bathes our planet, all whisper the same message. We are not apart from the universe, but an intrinsic part of its unfolding story. This perspective invites a profound shift in how we perceive ourselves, not as isolated individuals, adrift in an indifferent cosmos, but as integral players in a vast interconnected drama. This cosmic interconnectedness challenges the anthropocentric view that places humanity at the center of the universe. For centuries, cultures and philosophies have grappled with the question of humanity's place in the grand scheme of things. Some traditions elevated humans as the pinnacle of creation, while others saw us as humble stewards of a divine order. Modern cosmology, however, offers a different narrative, one that strips away ego and invites humility, the realization that we are made of recycled stardust, and that our lives are punctuated by the same forces that shape galaxies, forces us to reconsider our role in the cosmos. Are we the protagonists of this story, or are we a single line in a poem written by the universe itself? The answer, it seems, lies in the interplay between individual agency and cosmic determinism. Just as the elements in our bodies were forged in stellar furnaces, so too are our choices and actions shaped by the conditions of the universe. Yet within this framework, there is room for creativity, exploration, and the pursuit of understanding. This cosmic perspective also fosters a sense of unity that transcends cultural, national, and ideological divides. When we acknowledge that the same gravitational waves that ripple through the heart of a distant galaxy also pass through our own bodies, we begin to see the futility of drawing boundaries between us and them. The universe does not distinguish between continents, languages, or religions. It binds all matter and energy in an intricate web of causality. This insight can inspire a collective ethos of stewardship, encouraging us to care for our planet not as a resource to be exploited, but as a rare and precious node in the cosmic network. After all, the Earth is not just a cradle for human civilization. It is a repository of the same stardust that fuels the stars, a fragile oasis in an otherwise barren expanse. Recognizing this shared origin can motivate efforts to protect biodiversity, combat climate change, and promote sustainable practices that honor the interconnectedness of all life. Moreover, the cosmic perspective invites us to reevaluate our relationship with time and eternity. On the scale of the universe, the span of human history is infinitesimal, a blink in the 13.8 billion-year timeline of cosmic evolution. Yet within this brief moment, humanity has achieved extraordinary feats. We have mapped the surface of Mars, decoded the genetic blueprint of life, and detected gravitational waves that have traveled for eons to reach us. These accomplishments are not merely triumphs of technology, but testaments to the human spirit's yearning to understand the universe and our place within it. The pursuit of knowledge becomes a sacred endeavor, a way to participate in the ongoing dialogue between the cosmos and consciousness. In this sense, science and spirituality converge, both seeking to answer the fundamental question: what is the nature of reality, and how do we fit into it? This convergence also raises profound philosophical questions about the purpose of existence. If we are the universe contemplating itself, what does that imply about the nature of consciousness? Is our ability to ask such questions a fluke of evolutionary biology, or is it a necessary outcome of the universe's complexity? Some thinkers argue that the emergence of life and intelligence is not an accident but an inevitable consequence of the universe's laws, a natural progression from the Big Bang to the development of self-aware beings. Others suggest that our existence is a cosmic coincidence, a rare and fleeting spark in an otherwise indifferent universe. Regardless of the answer, the fact remains that we are here, capable of wonder and inquiry, and that is enough to imbue our lives with meaning. The cosmic perspective also encourages a sense of responsibility. Knowing that the universe is a dynamic system, constantly evolving and reshaping itself, reminds us that our actions have consequences that extend far beyond our immediate surroundings. The same elements that sustain life on Earth were once part of a supernova explosion. The same gravitational waves that reveal the secrets of the cosmos may one day help us navigate the challenges of interstellar travel. In this context, our choices, whether to protect the environment, to pursue peace, or to advance scientific knowledge, take on a cosmic significance. We are not just shaping the future of humanity. We are contributing to the ongoing symphony of the universe, adding our notes to a melody that began with the Big Bang and will continue until the last star fades. Perhaps most importantly, the cosmic perspective invites us to embrace mystery. Despite all our advances, the universe remains largely unknown, filled with dark matter, dark energy, and phenomena that defy explanation. This mystery is not a limitation, but a source of inspiration. The fact that we can observe gravitational waves and trace the origins of the elements in our bodies is a testament to human curiosity and perseverance. Yet for every answer we uncover, new questions arise, deepening our appreciation for the vastness of the unknown. In this way, the universe is both a teacher and a student, continually challenging and surprising us with its complexity. As we stand at the threshold of this cosmic understanding, the universe hymns on, its symphony undiminished by our fleeting presence. The gravitational waves that ripple through spacetime, the elements forged in stellar furnaces, the light from quasars that has traveled for eons, all continue their eternal dance, indifferent to our momentary awareness, yet strangely attuned to our capacity to comprehend them. This paradox of connection and detachment is at the heart of our place in the cosmos. We are both insignificant and significant, a speck of dust in the vastness of space, and yet the universe's most profound expression of self-awareness. The story of the cosmic orchestra is far from complete. New chapters await discovery, perhaps in the form of gravitational waves from the early universe, revealing the secrets of inflation and the quantum fluctuations that seeded galaxies, or in the detection of signals from habitable exoplanets, hinting at the possibility of life beyond Earth. Each revelation adds a new layer to the symphony, expanding our understanding of the universe's grand design. Yet for all the knowledge we accumulate, the universe remains a source of endless mystery, reminding us that the pursuit of understanding is as vital as the answers themselves. And so, the universe sings on, waiting for us to listen. With every observation, every experiment, every question asked, we contribute to this timeless dialogue, weaving our voices into the fabric of existence. What will the next movement of this symphony bring? Only by continuing to explore, to wonder, and to seek can we find out.